front end. Give me a sec. Okay. Okay. So right now, what we have been doing so far has been the back end, the ZK backend, right? So we have been. So you have a prover, and you have a verifier. These two are the backend, okay? So, but you need a statement that you want to prove. So usually in GKR, that is a circuit. So you need a way to be able to kind of like convert your computational problem into a circuit. Then you now pass that circuit to the backend. Now that thing, the front end is the part that handles computational problem to circuits. Okay, so you have some problem, and then you can go into like a circuit. Then you can now take the circuits and pass it to both the prover and the verifier. Make sense? So this part here is the front end, and this part here is the back end. But the output is just something that the prover can work with, something that the prover and the verifier can work with. So it depends on the proof system. That's what determines the exact output that one is going to work with. Now in this front-end space, there are multiple ways you can get that final circuit out. Okay, one way is to just write the circuit directly. Another way is to write regular Rust, for example. No concept of circuits. You just write Rust. And then that now gets converted into a circuit under the hood by a compiler. And the circuit now gets passed to like the backend. So there are really like two different categories. So there's the DSL, which is like a domain-specific language, right? Where you are now writing the circuit by hand yourself. So you are writing the circuit by hand, but then they give you like utilities that make that easier than normal, right? Then so like we already, all of us here have like some circuit representation, and we know how we write stuff in there. We have to put each, we have to know all the gates beforehand, and we need to now put them in. So that's like no utilities whatsoever. Then on top of that, there are now things that like give you a way to represent logic easier, but then it now converts it into a circuit. That's the DSL. Then there's now the ZK VMs.
So you said the DSL is like manually writing the circuit.
It's like you're still writing the circuit by hand, but then you have help in terms of like there are small functions that make the process less laborious. Does it make sense? And then you now have ZK VMs. So ZK VMs basically they have a language. So it could be Rust, or it could be Cairo. Okay? So you have a language that you can just write your code in. Then you now have a VM that can execute that language. So what they are basically proving is that the VM correctly executed this source code. Okay? So now you're not writing circuits again. The circuits have already been written on the VM side. What you're just writing is regular code. And then that just like gets passed to the VM, and then the VM proves that it ran that code correctly. Okay? So, hmm? So it's like you have a VM. What's a VM? A VM is just a machine that takes source code and then it follows the instructions in that code. So it's just following instructions in some source code. And at the end of the day, it's going to have some output. Okay? So you can write code to like prove Fibonacci, for example. Just regular Fibonacci. And then you give it to a VM, and the VM will just like follow the instructions and just execute it. So now what the VM is proving now is that it followed the instructions correctly. Does that make sense? So it followed the instructions correctly. That's what the VM is proving. So the circuit is now on proving the VM's correctness, not on proving your code correctness directly. Wait, let me just write this. So this is a VM, and then the VM takes the source code. So the source code is basically what the VM is going to run. Then this VM already is kind of like a circuit. So the circuit, this thing has been moved from here to here. So the VM itself is a circuit, or has been represented as a circuit. And then that can already be passed to like the backend. Okay? So what we are proving in this context is that the VM ran correctly given this source code and this input, which also means that your code has been proven. It's like indirections, yeah?
So how to understand? So we're talking about categories of presenting circuits.
Yes, of getting computation to the backend. Yeah.
So we have the problem with circuit there to so now this VM we have here,
Yeah.
this KVM is another representation of a circuit.
It's a circuit. Yeah, it will be.
Yeah,
It should.
it's a circuit.
It's a circuit.
Yeah, but so we have where you can DSL you have manually put in external external.
Yes.
So but the ZKVM now, it's a I'm trying to understand I'm trying to put in what you get not understand. Okay, so you have a code right now
Yeah.
that you are converting to what I'm trying to get.
So you just write. How do I put it? So for the DSL part, right? The entire goal is that you have some computation that you're trying to prove was done correctly, right? So it always starts with computation. Then in the DSL category, what you do is that you will now write an equivalent circuit that is the same as this computation. So you are rewriting the computation as a circuit. Okay? Let's say your computation was to add two numbers, a plus b equals c, right? What you do now is that you convert this to, this is a, this is b, then let's say your GKR, this thing is plus, right? And then it needs to be c. Then all you just need to do is just like check that c is equal to c. So now this circuit is an exact replica of your computation. And there are tools that allow you to take things like this and write them as this. We're going to look at one today for GKR specifically. Okay? But now, there's also another way to do this, where circuits have already been created, but it's a computation, right? Now the computation has changed. The computation is now execution of a virtual machine. That's the new computation. So this one was like inputs. Inputs were AB, ABC, right? In this other one, it's not like you have circuits for the VM itself. So let's say you have like something like this. Oh yes, so this is not like the actual circuit for a VM. It's much more complicated. So this has already been done. The circuit for the VM is already done. Now, what's the input to this VM? Your source code, right? So now this VM is going to take as input a plus b equals c somehow, right? And it's also going to take in what you actually gave a to be. Let's say like 1 plus 2 equals 3, right? It's going to take these two things as inputs. So you're not converting that necessarily directly to a circuit, the traditional way we know. We're just using an already existing circuit to run that. Those are now like the inputs to your circuit. Does it make sense?
So that means for the first one, like that, not like that's first instance.
Yes.
You're tailoring it. You're writing for a specific
Yes.
problem.
Yes.
But here you can throw in any
Computation.
into that.
Yes. So it's like one circuit to rule them all. So once you have your computation, it can run that computation. Okay? So now, the computation that most people do right now, like most companies, is like execution of the RISC-V VM. RISC-V. So the RISC-V virtual machine. It's basically like the way you have Intel, and so it's like an instruction set architecture that has opcodes. So what they do is that they take this RISC-V virtual machine and they build circuits that can prove the execution of this RISC-V virtual machine. Now, what can RISC-V do? RISC-V can take anything that compiles down to the RISC-V instruction set. So if you guys have done anything VM related, this will make more sense. But it can take any opcode or any set of opcodes that are like RISC-V compliant, and then the VM can basically run that. So a VM is basically just memory. So it has like registers. So that's like this is the memory, right? And then the memory has data inside of it. Then you now have instructions that kind of like manipulate this data. So for example, you can have like add to add whatever is at R1 with whatever is at R2 and store the results in R3, for example. So let's say this is R1, R2, R3. Let's say at the beginning, before this instruction was executed, R1 had 1 and 2 inside. But then R3 also like all the rest were empty. So by the time it runs this gets to this instruction, it's going to take the value at R1, which is 1, the value at R2, which is 2. It's going to add it all together, 3, and then it's going to go and update the memory with 3. Okay? Then it's going to see another instruction, which is going to tell it to do some other stuff. So it's just like this, all the instructions. By the time you're done, your answer is supposed to be probably in one of these memory locations. So the VM is basically proving that it did all of this correctly. Because there's a specification that, okay, if you see this, you should do this, right? So it's now needs to prove that I saw all of this and I did the correct things at the end of the day. Now, these are the trade-offs. Okay. Yes. So the VM has opcodes. So you're going to create circuits for each opcode already. So like the add now, there's already a circuit for it. The more, there's already a circuit for it. And all the possible opcodes, there are already circuits for it. Then you still have like a big orchestrator that knows how to call which circuits, when to call which circuits basically. So that orchestrator is basically going to take like the opcode instructions and then it's going to know how to call everything and proves that everything is working correctly. But the good thing is that once you have implemented all the opcodes, you can now take any RISC-V program and you just have one program that can consistently prove any possible program that you can create. And RISC-V is like something that Rust can compile down to. Okay? Not just Rust. Almost anything can compile down to RISC-V. So this means that now the companies that are building ZKVMs allow you to just write like regular Rust. Regular Rust. You don't even need to think about like fields and other things. You just write Rust. and then it takes that Rust, compiles it down to X5, which is basically a series of all these add. There may be more, there may be move, jump. It's like assembly, X5 assembly. Compiles it down to X5 assembly, and then that assembly is now passed to the ZK VM. Then that one just like proves every single thing one by one. Let me show an example of this thing actually.
Who's the verifier in this case?
So there's not going to be a verifier for the circuit also. Do you get? Yeah, so these are some examples of opcodes in X5. So you have the add opcode, sub opcode, that's like subtraction, XOR, or, and SSL. I think that was like store something. What was it? Shift left lower. I'm coming.
You have to implement the circuit for all of them.
Okay, yeah. Yes. So you have to implement a circuit for all of that. But it's a one-time work. Circuit. Wait, I'm coming. Yes. Shift left. What were we looking at? SL. Okay. Yeah, shift left logical. So this is the instruction, right? It's supposed to read whatever is in RS1. Is this it? No. It's supposed to read whatever is in RS1, and it's supposed to perform a left shift based on the value in RS2. That's like this thing here. So now, what you're supposed to do, not that's what companies are doing right now, but I feel everybody can do it. It's like you now take each of this, depending on your VM layout. So like Seno now, this one that was done on Scroll. This paper is no longer up to date based on like what is found while they were building. It's an example of how you could build a RISC-V virtual machine or any virtual machine at all. But this one is using GKR. I'm coming. So this is an example. So this is an opcode circuit for it. So this could be like your add, your SLL, all those, right? As opcode circuits. So there's something called memory checking. That's how you kind of like link everything together. Okay, but it's one-time work, right? You just have to build circuits once for everything RISC-V. Then once it's done, you can now prove any RISC-V program. ZK VMs too are doing exactly the same thing. So all the ZK VMs that you know, ZK EVMs, that's like Ethereum's virtual machine. It's just the same thing. But instead of proving RISC-V opcodes, they're proving Ethereum's opcodes. Okay? The EVM's opcodes. But it's the same idea. So basically what this is now is like the industry have figured out a way to like prove VMs. So any VM you can think of, if you know how to create like provers for VMs, you can create provers for any VM, whether RISC-V, EVM, maybe even like x86, Intel chips, anything you want. Make sense? Yeah.
Now this is ZKVMs.
Yeah.
Like specifically for this RISC-0.
RISC-V.
It's fine.
RISC-0 is a company that is doing a RISC-V ZK VM.
RISC-0 is specifically.
They were the first ones to kind of like do it at that production level.
You see that, like, from now on, show us your code, right? You wrote like a ZKVM.
No, I just wrote the VM.
You wrote the VM.
Just RISC-V VM, not the ZK VM.
But the ZKVM is already built, like it's ready.
But multiple companies have been working on like ZK VMs.
So like, I want to understand how it is used, like.
Right now.
Used, yes.
So you just need to look at like RIX zeros, or let's say SP1. Alright, okay. Let me see if they like allow you to. Let me see. What's there? So yeah, this is an example, right, of building something with the VM. It's still just almost regular Rust, right? So this now is like inputs they are getting from the user. They are trying to multiply, I think, two numbers and ensure that um, trying to multiply two numbers essentially. So what it is that you have A as a U64, you also have B as a U64. Then it's like if A is equal to 1 or B equals to 1, trivial factors. So it doesn't want you to multiply one of it doesn't want any of them to be a 1 basically. Then here it's not like computing the product. So A dot check more B dot expect integral alpha forever. And then once it does, it just commits it to the output. I think there are better VMs right now that make this, because right now it's like very so this is the idea. It's just like you write regular Rust. They have a tool chain that compiles that Rust to RIX5 opcodes. Then they pass that to their ZK VM that just wants opcodes. And then that one would basically prove that that is correct. It's like whenever you have something called a trace. A trace is just like you're writing down all the steps that you took. So the prover will first of all generate the trace. So given the opcodes, the prover is basically going to say, okay, this is what the registers look like when I started. Everything is empty, right? Then I saw the first thing. Maybe these two reads will put A at register something and B at register another thing, right? So you need to write that, okay, I put this value here and I put this value here. Then next thing you're going to see is probably, let's keep this multiplication, right? That's basically saying that, okay, take the value that you put here, take the value that you put here also, multiply the two of them together, and store the results at product. Maybe that'll be another register location or memory location. Okay? So it's going to say, okay, I did this, I took this, I multiplied this, I stored this. It's going to do that. So it's generating the trace. It's telling you exactly what it did at every step. Then once it's now done, the backend will now take this trace and now verify that everything you said you did, and you also did it correctly. So you said that you took something from A, and let's say, well, what was that A was 5, but then what you now used in your program subsequently was 6. That means you lied. You didn't really take 5 from A's location. Something is broken there. So the prover is not supposed to give you no, the verifier is supposed to catch that oh, something has happened, something wrong has happened. Does that make sense? So you just do like this for the entire VM, and then the VM just takes that trace and then just like proves everything.
So, you write the VM, after the show, write the VM, right? Now, you pass like that, you compile it down to this 5 instructions.
So wait, what I showed you now was just us trying to understand how RIX5 works. Not necessarily like, oh, this is now a VM, or this is not a ZK VM, right? So once you understand how RIX5 works, you will now use that code, for example, to generate the trace if you want it. But I think you have to tweak it a bit. So it's like you give it source code, and then it now has the ability to generate a trace.
This is the ZK VM they are giving this.
The VM, there's something called an emulator. The emulator is basically going to take the RIX5 assembly and generate the trace. So this Seno Emu, right? This is basically emulator. So what they do is let me see. What did I just open? Platform, steps, step. I'm looking for step records. Okay, yeah, so see this thing called step record. This is basically what is keeping track of everything that happened in the execution process. So it's like, okay, what was the cycle? What was the program counter? What was the instruction that I was executing? What was the value of my RS1, my RS2? What was the value of my return? That's like where I'm going to write my results. That's like destination. This S1 is source 1, S2 is source 2, and D is destination. Then memory up. Did I write? Yeah, what kind of memory operation did I perform here? And then syscall. Sometimes you call, there's something called syscall where you break out of the VM and then you call something on the host. Like let's say you want to print to the terminal. The VM doesn't have that, so it tells the host that you should print to the terminal. So now this is like one line of the trace. Then when you run the emulation, you're basically collecting a vector of all this, and that's not going to serve as your entire like execution trace. Now this entire thing will now be taken and fed to the ZK VM. Then the ZK VM will now prove that each of those steps were done correctly based on the previous state. And then it keeps on proving this until it has proven all steps are consistent. And then it generates like the full proof and sends that. So it verifies that proof and it's good. Then that means that from the first step to the last step, everything was consistent. If you make any mistake, let's say you're supposed to add two numbers, but you subtracted, the verifier will not verify correctly because of one of the opcode circuits will be broken.
Sorry, I'm lost.
You came late, that's why. So we can't just like go all the way back. We're just talking about like ZK VMs, you know. Okay. Makes sense?
Not when you like
So I want to know, does it mean that ZKVM allows us to generate, for example, like maybe like for particular protocol, let's say like ETL, another protocol, just another ZKVM for another protocol, or just
So the ZK VM uses it has its own backend. So like different ZK VMs have their different backends. So like Seno now, the backend is GKR. Okay? Then Cairo is a ZK VM for the Cairo lang. So that will compile down to assembly. Now Cairo, the backend is stacks. Okay? So that's the backend there. So the ZK VM takes the assembly and then converts it to a form that is suitable for their backend. Okay?
so that means like wait, you mentioned now Cairo. Cairo is a ZKV.
Yes. So there's something called Cairo VM.
Cairo is
I thought it was mentioned that ZKVM generates proofs that when it generates proofs that
It-
verifier can work with to verify whether everything is correct.
Yes. So the ZK VM, every VM, ZK VM has its prover and its verifier, right? So the prover is proving that you ran the VM correctly. That's like giving this assembly, you did everything you were supposed to do inside of the VM correctly. Because the VM just takes assembly and then it just changes things about its state. Like it has registers and it has memory. So if you see something that's supposed to load into a particular register location, it's supposed to load into that register location. So that's what a VM is. Now there are now different types of VMs, right? So like there's the Cairo VM, then there's the RIX5 VM, then there's the EVM. It's everything. Like every VM always has a specification for its opcodes. Right now, almost all the ZK VMs are using RIX5. as the VM that they're trying to prove. So like Seno now is using, they have a RX5 emulator. SP1 too, they also have a RX5 emulator. RIG0, they also have their own RX5
Everyone is
emulator.
a VM.
Yes, they have a VM too.
So sorry, you said VM takes in assembly. So is it like it takes in the assembly like those things you are working with polynomials? So is it that it takes in those assembly like how does it take them like assembly? How does it take them before it approve and verify?
I'm coming. What will it be actually? I'm trying to find their emulator. Probably in core. Okay, yeah, see executor. They call their own executor. So let me see. Okay, ALU. So see RIX5. So see theirs now, right? It's still the same, like let's still add the shift left, shift right, AUIPC. So it's like you can see here, right? So all of them have ZK VMs. Yeah, Cass, you were saying that so yeah.
So this is what it takes.
No, you were asking what does what? The VM.
Okay, you said the VM
Yeah.
takes in like
Assembly. Yes.
right?
Yeah.
So like taking in assembly,
Yeah.
what does it like? How does it take the assembly? Is it like there's an arithmetic? That and practice that. Is there like there's an arithmetization technique that happens on the assembly before it does this thing like to convert it to the
No. It's more like okay, so for each opcode you have a circuit associated with it.
for each
Opcode.
opcode. The opcode you're talking about, opcode with regards to
Like add. Like RIX5 now, these are all the opcodes for the base instruction set. So these are all the opcodes. So add, sub, XOR, or now all these opcodes have associated circuits with them. Or in Stack World, they have constraint checking polynomials. That's polynomials that can check that these operations were done correctly. Okay? For each of them. You know, the one that will check whether it added two numbers correctly is different from the one that will check whether you multiplied two numbers correctly.
and every assembly is a representation of opcode.
Yes. It's like assembly is just a set of opcodes.
Opcode.
Yes.
So
And their
that
inputs.
means, so if every assembly is a representation of opcodes, that means each opcode you say each opcode has a circuit. Each
In
opcode
GKR,
is
yes.
a
Yeah, in
circuit.
yes, that's a circuit.
So that means if you're running computation, the computation will be running based on the number of opcodes.
Mm-hmm.
If opcode is a circuit,
Mm-hmm.
let's so because GKR
Yeah.
this circuit, evaluate the circuit, then run this thing. So if every
Opcode.
every assembly like it's a language that is made up of opcodes,
You
right?
just have a series of opcodes,
Yes.
yeah.
And each opcode has a circuit. So that means GKR is going to run based on the number of opcode that makes up a particular algorithm you wrote.
You're saying that you're going to run multiple GKR
Yes.
distance. So yeah, it depends on how you structure it. So like Seno, what Seno did was that Seno took all the, so you have a series of opcodes, right? GKR is really good for something called data parallel circuits. That's like when you,
What?
Something called
data parallel circuits.
okay.
That's basically like you have the same circuit, but then run multiple times, but then different inputs. That's the only difference. The circuit is still the same. You see?
So it's used for
No, it's you. That's like the superpower. That's where like you can like. That's like what people want to use GKR for. If they can figure out a way to represent their computation in a data parallel way, it is like really efficient for those kinds of computation. And that's when you are doing the same thing over and over and over again, but then the different inputs. So let's say like you're adding 15 numbers over and over and over again, but the 15 numbers are changing every single time. So how Seno now did this is that they now said, okay, we're going to group opcodes together. So all the add opcodes, we'll group all of them. All the mul opcodes, we'll group all of them. All the so it's like your computation normally is like I'm going to do add first, then I'll do mul, then I'll do another add. Then I'm saying we're going to rearrange everything and do all the adds together, do all the muls together. That now takes advantage of GKR's data parallel superpower, right? So they prove all of that at once. So one GKR proof there. Then they prove all of these other ones at once. Another GKR proof there. But they still need to somehow prove that add was first, then mul, then add, right? So that link still has to be there somehow. So what they now use for that is called memory checking. That's where lookup arguments come in. So they use something called a memory checking argument that allows you to prove that you collected something from the memory and you added something correctly to the memory. So that's like the memory checking argument is the link between. So you can see it here, right? Opcode circuits. It's like let's say all the adds have been done here. Then this one maybe like all the muls have been done here. But then see the consistency check here. So that's the one that is going to now link everything together. Does that make sense? So this DP here, yellow, data parallel. So that means that this is data parallel, this is done data parallel. So that means that all the things here are kind of like the same, just different kind of like inputs.
So if we are building a ZK
EVM.
sorry,
Or
ZK
it doesn't. It's all the same, yeah.
If we are building a ZK now, what is our goal? Like, our goal is to move from point A to point C. What is that point A and what is the point C?
The point A is that you want to take the assembly of your VM. Okay?
Okay.
That's like the inputs to your circuit.
Okay.
It's like GKR, where you have a circuit and your input is the input layer, right? What's your goal there? You want to prove that. So the prover is the one that is going to do the execution of that circuit, right? Until it gets the output. And your goal is the prover wants to prove that it did this execution correctly. And then it's going to generate a proof of correct execution. Then you're going to verify that proof. All good, right? Now, similarly, in the ZK VM side, there is a circuit, which is like the VM. Then the input to the VM is the assembly. The same way you had the input layer. Your input layer, in abstract terms, is the assembly. Then the prover normally can run the assembly on the VM and get its output. So then the prover now needs to prove to the verifier that it ran this VM correctly to get this output. So you run this VM correctly, giving this assembly to get this output. That's the idea.
So now, irrespective of how the assembly comes, doesn't matter.
Doesn't matter.
Even if you're using Cairo, Cairo combines to, let's say, Sierra, so that might be the
There's cousin,
assembly
right? Yeah.
that they are working on. So like for assembly.
It's cousin now. CASM.
Okay,
Cairo
yeah,
assembly.
yeah, Cairo assembly.
That is Cairo's assembly. But now it's like the VM does not care about the assembly. It doesn't give me any assembly that is any Cairo assembly, right? And I'll execute it
So that means anything you're doing has to compile down to
to assembly. Yes, yes.
Oh, okay. And Rust compiles down to what?
So now there's now Rix 5.
Yeah.
So Rust can compile down to Rix 5 assembly.
It's that one.
Yes.
Okay.
Rix 5 assembly is just like this one. So
So now-
it will be opcodes, I guess.
So now since every opcode has a circuit.
In Seno type design, yes.
Okay, Xenotype design.
Yes.
Oh, Xeno. So in Restyle design,
Rix 5 is not a proving system, it's not a backend. Rix 5 is just like an instruction set architecture, right? It's just like chips, it's a chip specification. Okay?
Another example like this.
Like x86.
Sorry. So you said
Eh? And 6, yeah, that's like the. So there's risk and 6. That 6 is like, I think it's like complex instruction sets. I don't know, I'm not sure. But Rix is like reduced. Yes. So yes, complex instruction set computers. So in complex instruction set computers, they have a lot of opcodes, like a lot of opcodes, to make your life easier, right? Let's say you wanted to do one crazy division, or let's say you wanted to do matrix multiplication. It's possible that they might have an opcode to just do matrix multiplication. But matrix multiplication is just, if you really condense it down, it's just a series of multiplications and additions. So the Rix 5 versions would not put matrix more as one of their opcodes. They will put adds and mores, but a lot of it, right? So that's the difference between SICK and Rix. But they still kind of like they can still compute the same thing. It just one's assembly will be way longer than the other one. But the good thing is that for Rix systems, the chips are more efficient because they don't need a lot of components. Because every opcode is kind of like almost a component on the hardware. So if you have few opcodes, then you probably have few components, which means that you don't need as much cooling, for example, or as much this. But then it's not as convenient, maybe.
so. Just take it back a bit. You said each of these.
We're supposed to build
Operation.
expander circuit. Now I look at. I thought we're supposed to build expander circuit. Now I'm looking at how to build ZKVMs. Yeah, continue.
So is it each of those
Opcodes,
operations
yeah.
is a circuit?
Could be,
Now, when
yes.
you say each of them is a circuit, do you mean like taking that GKR circuit, for instance? You know, in a circuit, for instance, we have add gates, we have more gates. So now, when you say each operation is a circuit, do you now mean like a circuit made up of add gates only, and then a circuit made up of more gates only?
It could be, or it could be a mixture. Like, your circuit is just like you just combine the add gates and the more gates to create some computation, right? So it's the same thing. It's more like you have some computation that you're trying to represent. Let's say add, sub, more. Those ones are simple, right? Just the regular add gates, more gates, that's fine. But then when you now start getting to more complex things like store or load or shift, then you're not going to be having computations that make use of more than just only add or only more. So it's not circuits that are using more things in it. So each of them is just like you have a circuit that can take in the inputs to the add or the mol or the left shift or the right shift, and it can prove the answer is correct.
so if you say you want to build a VM now,
A VM,
yes.
separate, just a VM, not a ZK VM.
Okay, let's say we want to build a ZK VM.
Uh-huh.
What should we look at? Like, what's our go-to steps?
First, you will need to understand VMs, right?
Yes.
So you probably just try and build a VM. I sent the LC3 VM to you guys to try and build. That will give you, it's very short, but it will give you most of the,
Oh, that's fine.
yes. And if you know that, okay, your target is Rix 5, it might still help to go and try and like build a Rix 5 VM. But once you now know like, okay, how VMs work, next thing you need to look at is how people make VMs Zikified, yes. That's probably reading papers, okay? Yeah, there's Seno paper, there's Jolt paper, SP1 is just using like stack Cairo VM paper. There's also the Cairo paper. I think there's the Cairo paper. Yes. But this one is using like a stack backend. So then there's Jotes also. But this one uses a lot of like lookup tables. Okay. So you now need to go and look at, okay, what does the literature say about this currently? That way you now start getting a sense of how different people approach it. Then you now decide on the approach you want to take. So you decide to take one of the already existing approaches. Or you could decide that, okay, I have seen enough. I've extrapolated and I want to now build my own version of this ZK stuff. And then and then you now do that. Does it make sense? So you just understand VMs first, understand how VMs have been Zikified in the past, then now use that to know, to choose how you want to do yours. But anybody that is interested in doing something like this, we should talk. It's only GKR circuits, son.
Yeah.
It's only GKR circuits.
What you said?
Only GKR circuits.
Okay, you only need GKR circuit.
You said can any circuit?
Can any circuit, you know, since all those things are circuit now, we can just pass in into our GKR. Okay,
It has
but
to
we
be
don't have the same structure.
exactly. It has to be exactly the same structure with you.
So you were making a statement, say anyone interested in
Yeah, anyone interested should just reach out. Anyone interested in like getting a ZK VM, like find out ZK VM, should reach out.
is it after doing that LC3 or before or no?
After doing that's like the permission to reach out.
LC3. That
I sent a VM paper on,
paper.
not a paper, a tutorial on WhatsApp.
Okay, alright. Okay, that's
Okay, you said it's
okay.
tutorial
That's the
for
VM.
it,
To build the VM.
Yeah,
Mm.
I've sent a lot. I'll send it again.
In
If
the,
you guys
in the
can.
WhatsApp group or Telegram.
WhatsApp.
So we have VM, we have ZKVM. So every ZKVM has ZK or this one
Zikified.
has ZKified
A VM, yes. Yes.
So so at every point that so a ZKVM always proves a VM.
Yes.
Right?
It's proving the correct execution of a VM.
So for instance now, let's say a ZKVM that has ZKified a RISC-V VM. Right? So the RISC-V VM has its own codes. So let's say a program now, right, a host program was run, right, after it, okay, in the process of running it, they run it on RISC-V, in the sense that they compiled it down to RISC-V
Assembly.
codes,
Mhm.
RISC-V assembly, then they run it on the RISC-V
Emulator.
emulator. Then after they run it, they had that
The
is
trace.
the
Yeah.
right? So it's not that trace that you passed to ZKVM.
Yeah.
So what you're not saying is that, for instance, now let's say our ZKVM is using GKR.
Yeah.
So meaning to have circuit that
For
represent each of those
Yeah.
things. So it's not going to so while that trace is going to help us feed
Yes.
those circuit their inputs and their outputs.
Yeah.
Okay. So my question now is, since that trace helps us feed it,
Mhm.
is it not possible to run? Why can't you just take this 5 opcode and run it directly on the ZKVM?
No. It's kind of like what you're doing, but you're adding more information to the trace is giving you more info.
Well, what you said was that the opcode will first run on RISC-V, which will generate the trace.
But it's not the trace, right? The trace had the instruction. It had the PC. It had the instruction. It had the. It had like more info about that round that you ran. You know, ZK is not necessarily always trying to prove. It's always trying to like perform the competition itself. All ZK cares about is that I'm showing you that this competition was done correctly, right? Like if you want to divide two numbers, it doesn't make sense to do that inside a circuit.
Okay.
Instead, what you should do is that you should take a hint. That's like from. I'm coming. So rather than implementing division directly, instead what you should do is, let's say you wanted to do A divided by B.
Oh.
What's going on? Yeah, you wanted to do A divided by B, right?
Mm-hmm.
And it's supposed to be equal to C.
Mm-hmm.
Instead of doing the division, thing inside of the circuit itself, what you do is that you now use a multiplication gate instead. And then you say, okay, give me the value C. And then I will now check if it is equal to A. Do you get?
Mm-hmm. Yeah.
Like, it's expensive to express something like division in a circuit. So instead, you say, go and do the division outside. When you have gotten the answer, I know how to do multiplication easily inside of a circuit. So when you tell me what the actual division is supposed to be, all I need to just check now is that B times C is equal to A.
Okay, so this KVM does checks.
ZK. The goal of ZK is to check that the computation was done correctly. That is like a very flexible position to be in the sense that you don't have to do the computation exactly. You can instead use hints where you need to use hints. Obviously, you can still do all the computation yourself, right? Like you can express the division in a circuit. It's to be a crazy circuit though, but you can do that. But then your circuit is going to be bigger, meaning that your prover is going to run slower. So now, something like this now is like the prover did some things outside, got some hints, and then those hints are now basically used. So those steps now, for some opcodes, they put the relevant hints that are needed to help the prover check this thing correctly. You get? So there might be a div opcode. So now in the div step, there will now be the C there also. So when it's now time to convert that step record to the circuit that will prove it, it will now take the C from the step record and put it there.
Okay, so that means that in the actual circuit, after you check this, you can also do the division.
No, no.
Let's say, I'm just saying for instance now, let's say it checks A over B is equal to C, right? So when it checks that B times C is actually equal to A,
Yes.
in the actual circuit of the division, you can now say A divided by B is 6.
Yes. Like that's like it has confirmed it.
That's yes,
Yeah.
that's confirmed.
And it needs to confirm all steps basically.
Okay.
Yeah.
Can we go back to
Hmm?
Can we go back to where we're coming from?
Don't worry, we'll get there.
I don't understand where we were before.
Don't worry. Any other question?
Yeah, I still have questions.
What was the question?
So, this one,
Yeah.
yeah, I remember a time that, okay, yeah, so relating to our current implementation now
Of GKR.
of GKR, right? So that means that our circuit itself,
Yeah.
right, is something like this 5.
Hmm?
No, I'm just making an analogy.
Okay.
So, with our GKR circuit,
Mm-hmm.
right, our GKR circuit currently just proves, okay, we prove, right?
You prove correct execution of a
Yes.
circuit.
Exactly. So what I'm saying basically is we run evaluate on our circuit
Yes.
to generate the whole thing.
Yes. All those intermediates inside like the trees.
Yes. So what I'm saying now is suppose I'm saying that's what with 5 goes to evaluate it.
That was VMs.
Okay, yes, that was the VM we do to run the evaluation. Then our GKR
Prover.
generator is
Yeah.
now the prover,
Yes.
right? So it now generates the proof from all those things.
Yeah.
Right. So now the only difference now is that we are assuming that the evaluation will come from it. There's no check.
Who is assuming? GKR?
We are assuming.
How?
Like the prover is assuming that the evaluation. The prover
The
is not
prover is the
doing
one that is
checking.
doing the evaluation.
That
Right?
is in our own instance, but it's not supposed to be the one doing it.
No, it's the one now.
This is, like what we just said was that you do the evaluation outside.
The prover will do the evaluation outside. Then he will now prove that he
Prove
did
that
it
he
correctly. Yeah.
Okay.
Or if it's malicious, he will try and come up with a proof that he did it correctly, even though he did not do it correctly. But it's more like, I don't want to run this VM.
Inside.
I don't know, me as a verifier, I don't want to perform this VM execution. You on your end do it. So you first of all do it outside to get all the relevant, just to make proving it easier. The same way when you can run your circuits and you get all the W's outside before you even start proving.
Yeah.
It's something similar. So the prover will run the VM, get all the trace, and then now prove.
So the prover running the VM is basically RISC-V.
You just use the RISC-V
Executor.
emulator. Yes.
Alright. Then proving is the actual is the ZK part itself where we are trying to prove. Then so I remember a time we were talking about there was a time you told us about circuit specific something like that.
Second person rule.
Yeah, I don't know how you describe that. It's something like if you want to build if you want to build a circuit, there's a general one, then there's a circuit specific one. Papa was mentioning that day, and he explained it. I've forgotten, I can't remember it.
There will be a term that you mentioned that will make you remember. That one is today. It seems we are talking about another day now. Alright.
No, it's not this one.
Not
I don't
today.
know what DSM is. But we're talking,
today.
you mentioned this one before, the tomorrow plan, like general and specific. Something about you can build a circuit and so it's related to this computation thing. Yeah, it's related to this computation thing and VM, right? This computation only works for a particular computation, and the VM can run any computation. So I was relating to something you said before in the formal class, something about circuit being specific and being general.
It's probably still the same thing. But now it's like, just say the VM can prove correct execution of a virtual machine, and it takes the assembly as like inputs, right? Then it can prove any assembly without changing your circuit. The circuit is still the same circuit. But now with this DSL side,
What's the meaning of DSL?
like domain specific one.
Okay, yeah.
What's happening here is that you are creating a very specific circuit for your very specific computation.
That's what we do with GKI.
That's what we're doing with the Okay? And that, if you want to change your computation, you need to change your circuit. So I change your computation, I change your circuit. So you're generating a new prover, a new verifier, a new prover, a new verifier for every type of computation that you want to do.
Okay.
Does it make sense?
Yeah, that makes sense. So my last question. I remember you said something about in Seno, right? They do outputs.
Data parallel.
Right. So each output has a circuit. What data parallel was?
Data parallel, like data parallel proving. It's kind of like you have circuits that are just the same. Like you use the circuits multiple times there, but on different inputs. You can prove it all at once.
So the way I was thinking about it when you initially explaining it was, okay, each output has a circuit, right? Then we're just going to link them together.
Then each output has a circuit, but then you now called add like 500 times in your assembly. So it's still the same add circuit, but just different inputs.
Yeah, so
you prove it all at once.
So okay, fine, right? Now layman, simple mind, never reach. And so what I thought was, okay, even if we have 500 ads, right, you can still have 5,000 whatever, right? So what I was thinking was, okay, let's say it was a simple circuit now, A plus B, then C times D, then whatever. What I thought was, okay, we're going to have the more circuit here. Then we'll now link the output of the more to the inputs of the add circuit, something like that. Then everything making up to an output. Yeah, something like this. So this was
And this is one circuit.
So let's say this. So what? Can you give it an output?
Let's just say jump.
So let's say this is jump.
Yes.
Then check there is okay, there's no EVM output. I know. So
it doesn't matter.
It doesn't matter. So let's say there's stop. Stop now has its own circuit.
Yes.
Right. So what I was thinking was, if the first instruction was jump and the next instruction was stop, we'll link the input of jump with so the output of
You need
jump
to link
with
so,
input
yeah.
of stop.
Mhm.
That was what I was thinking until you now said you can.
No, so you need to, they have to be, you have to prove the order too,
Okay.
right? But then you prove it from memory. Like they're only
Oh,
related from memory, kind of,
okay, yeah,
right?
yeah. Since they take their inputs from memory.
And then they store into memory. So you
So-
prove. So there's another branch that's really interesting also called like memory checking. That's what handles proving memory, then lookup arguments, read only, read write. So there's another branch that does like memory consistency checking. So they merge those two, the opcode circuits and also like the memory checking. So achieve like the fools given these days.
Yeah, so quick one on this one. So meaning that even if we have a jump operation, does not mean that it has its own special symbols and so we can still use this addition, multiplication, so long it does performs the jump from one point to another point.
Mm-hmm.
Oh.
So that means that this is risk. But if it was CISC, it would be one jump operation.
No,
Eh,
no, no.
uh-huh.
Whatever your opcode, whatever your VM is, has opcodes, right? All those opcodes have circuits. The only difference between RICs and SICs is that the opcodes are now more, you have way more
Way more.
opcodes, but all of them still have to have their own circuits.
circuits.
Yeah.
Like, now, we're talking about something memory programming. There's parallel circuit, data parallel circuit.
Yeah.
Right? So now, instead now, I want to know how they handle like, okay, let's say you're doing a very simple computation, like let's say 2 plus into brackets 3 times 4 divided by 2.
Mm.
Something like that. So now you're saying that we calculate all the addition, multiplication,
No, first of all, that computation that you just talked about will be expressed in RICS 5. RICS 5 only has like add more. So what did you say?
let's say you have plus 3 into bracket 3. Like the 3 is in several brackets. 3 times 4 divided by 2.
Everything right? So
No,
just,
just 4 divided by 2.
so this is just 2 now. But yeah, no, don't worry. No, just
That's like this here. And let's say times into bracket 4. 4 plus 3 into bracket 7. Like, you know, something like complex, like you follow
this.
things of,
So this entire thing now will compile down to just regular RICS 5 assembly. Okay, so I also the board master. I'll say like this one now, right? There'll be like an add, right? 4, 3, then store that result somewhere. Just say 01, right? Then this other one is kind of like you do the div. So you do div 4, 2, store that result in 02, right? Then now you have 02 times 3, right? So it will be more 3 with 02, store that in 03. So this entire thing now is 03. Then I'm supposed to do 03 times 01, right? So that will be more 03, 01, store in 04. So now this entire thing is 04. Then you now do add 2, 04, so the output in 05. That thing you just described will be this, something like this in assembly. Then you just prove it regularly. So you have opcodes for add, opcodes for div, opcode for more, opcodes for more, opcodes for add. So they'll just make, instead of that, they'll take these two, prove them together. This one will prove, and then they'll take this one and prove them together. Then they will now link everything through memory. That's where the memory checking comes in.
To see the correct, even though they are picking the first.
Even though it's out of
The
order,
last.
yeah, that's where the memory comes in. They prove that all of them use the memory correctly.
So I would see your definition of circuit for our complex system.
You said?
So I assume the definition of the circuit or the complex system.
Yeah, the decision of the inputs to the circuits. Yes.
Input or the no input then the no it's not input because the resolution of the circuits. Not the circuits.
It's not just, it's like how to orchestrate the circuits. So you already have like circuits for add, right? That knows how to take two things or three things, right? And check that everything was kind of like done correctly.
Yeah.
So when it sees this add and it sees this add, it's like it's not going to like put those add circuits side by side and then run GKR on this to generate like an add proof or something. And then it's going to do it for all the different opcodes. So it's going to know how to arrange all this based on the assembly. Like if there was no add now, there will never be any. So that's kind of like the, let's say, inputs now, or the orchestrator's input.
Not necessarily input inside, like input technical input.
It's more like how to. It's more like how to. Arrange things, and that's just saying no.
But this is
Yeah.
just a definition of one circuit.
Which one?
This
This old thing.
look at like you repeated this equation.
Yes.
This like
That's a program.
program.
That thing on the top is a program. It's like your Rust program or your Cairo program. So when you have your program, you now compile that your program into assembly. So that is one circuit if you are using, let's say, like the DSL routes, where you map it directly to an equivalent circuit for that computation. But this one now you're using the VM routes. So it compiles it down to opcodes of that VM. Then all those opcodes have their own circuits. So in VM land, there's no like big circuits. It's more like circuits per opcode. So you compile any program down to opcode, exactly. Yes.
How will this now be? You know, we're trying to do this so you can get like values for our GKR protocol operation. How will this now translate to that? I mean, I presume that our GKR level is just two values,
There's no way your GK will build so.
Now you say that this is just this circuit. I mean, they have small circuits, right? How would now according to what you said earlier, this is going to be used for our GKR operation. For instance, GKR is not used in the assuming that the protocol of transport is not going to be 4 to GKR, 4 to this.
So the prover, right, would have run the circuit outside. The VM outside, right? And will have generated a trace. So the prover is actually going to know what that O1 is. So that O1 is supposed to be 7, right? Then you now have a GKR circuit that knows how to check the addition of two numbers. So now you're going to tell that GKR circuit that, okay, I added two numbers, 4 and 3. And the expected output is supposed to be equal to 7.
Yes.
So this is like the circuits.
Okay, so that means that it's not going to be an elaborate circuit that we were used to.
Smaller circuits for each opcode. Exactly. So you now have another one here, right? 2 plus 1. What is 04? Okay, what is this now? This is 2, right? Then this will be 2. So what would this be? 6. Then this is 6. This is 7. What would this be? 42. And this is 42. This will be 44, right? So you have another one. So the add also is going to have 2 here. Then it proves this. Proves all the adds together. And that's add. Then div. Then more, 2 mores to prove them together. That's the more proof. But then also it needs to like make sure that the memory was done correctly. So the add was supposed to take that 4 and 3 from somewhere. It was supposed to add them and then store the results somewhere. So there's another protocol for proving memory. That's called memory checking. So when you combine operation circuits with memory checking, you have a VM. Operation checking. So like you're checking that every operation was done correctly. If you combine that with memory checking, then you have a VM.
That's always the case for VM.
For almost all VMs, yes. You know that the way they do their operation checking kind of like changes. So like Stacks now, the entire operation checking is like on a big table. There's no small this, small that. It's like it's all on a big table.
For stars.
So like one example of this is like you have a table that has all the registers or all the memory cells here. Kind of, right? And then you now have something called selectors. So selectors, you now have every opcode here. So if there's a 1 here, then that means you're doing like an add operation, right? So that will now know that, oh, I'm supposed to take a value here and take a value here, and I'm supposed to add two of them together and store it somewhere else. But this is just like stack. So you just, once you understand like how the stack protocol works, this will make more sense. Make sense? Yeah, let's continue. Let's go back to where we came from. So that's ZKVMs. So what that means now is that you can take Rust code, right? You just write your ZK thing in Rust. It will compile down to RISC-V assembly. Then to pass that to the emulator. The emulator will generate the trace. And then the trace will be passed to the prover, who will now prove that everything was done correctly, plus memory checking and everything. And then you now have like a proof of this Rust program. But then it's as simple as just writing regular Rust.
So is it possible to say an example of trace?
An example of,
Trace.
I showed it now. What did I use? Yeah, this is an example. An example of the what? Can you see it? Yeah. So like every step in the VM, you create one of these. So at the end of the day, the entire trace is just like a vec of step records. So this is like the PC, the current program counter. Then this is the instruction that was done at that point. Then this is what it read. Then this is what it wrote potentially. Because some instructions do not require you to read anything, and some do not require you to write anything. That's why it's an option. Makes sense? So you just have like a vec of this. Now, that's the VM side of things. So all you just need is to just write Rust or write Cairo, and everything is good. Now there's now the DSL part of things, where you're kind of like writing the circuit yourself. So anybody that's building a ZK VM needs to know how to do the DSL part, because it's the DSL they are going to use to implement all those, your add, your mul, your jump, everything. You're going to have to write those circuits by hand. The idea with all these things is that only a small group of people will write all the circuits, so that a larger group of people can just focus on writing Rust. Does it make sense? But then the actual companies that are building these things are writing like circuits by hand,
What is DSL?
like domain specific language, like a language specifically for just like
Circuit,
circuit construction.
like second.
Yeah, like Circum, exactly. So like an examples of this are like Circum, then
Skyro part of
Terra is more in the side.
the language.
Then let's say Rust, for example. Because they have ZK VMs. Huh?
Second.
No, like the one on top of Cairo.
That's ZK VMs.
you're calling Cairo and Rust.
They're kind of like languages that compile down to. So this is wrong, right? It's like I'll call it maybe like ZK Cairo and ZK,
It's V.
right? So anything that can compile down to X5 assembly can be proven with this.
Okay.
And anything that can compile down to cousin can be proven with this. Yeah. It's a VM. Cairo is a VM, right? And then the language that you use, there's Cairo VM, and then the language that you use that the VM runs is Cairo assembly, right? So Cairo compiler to cousin, and then cousin to this. So it's probably that DSL is such a general term, because it's just like a language that is for a specific domain. So maybe we should find another term for the guys that are here.
Can you do something like Cairo land
Mm-hmm.
and arrow
Mm-hmm.
to Cassism and
Cassism.
arrow
You want that at gas?
to
It's
Cassism,
There's no gas inside.
Cassism, then to the ZK Cairo or Cairo here. Then you now have the one for Rust to
So-
WebAssembly.
No.
To what? Then to what?
It's also still possible, right? But then there's now like
I used to call that thing Cassism and Wasism.
so there's a company that has done ZK Wasm also. It's still the same idea. They're just making a VM for opcodes. Uche.
Please, if it's not too much,
Mm.
I'll say something on top. Can you?
It's too much. I'm sorry. It's too much.
What
All these things, yeah, it's too much. Because it was so haphazard. So not like it was being lectured. Makes sense? So now, building the actual circuits.
More second.
Like Secom, for example, or Noir. But also today we're going to use Expander.
Expander too, so down to say domestic.
It's like, yeah, it allows you to build circuits. It's closer to what you guys have built already. Because it's also GKR based.
Oh,
But then it has a nicer front end that allows you to build the circuit. Right now, your circuit, you have to do like a vec of gates,
yeah.
and then you have to put like the IDs. This one kind of like handles that for you behind the scenes.
Yeah.
Yeah.
Sorry, before you, are we still going to look at that benchmark that we did?
Which one? You want to benchmark your code?
Benchmark.
You want to benchmark your code?
Everything.
Oh yeah, I know. We'll
So-
look into that.
That front end you're saying, can you go to the page, something like that?
Which
The one
page?
you said has the layout already that just it builds the circuit depending on the.
And that's what we want to do. And that's what we're going to do next. That's what we're supposed to do today.
Today,
We're going to do today.
yeah,
How we're going to do today. Cool?
So just give me.
There's no overhead, bro. There's no overhead, bro. Don't worry. Don't worry, it's not needed. It's not it's not needed to understand what we want to do now. So let's look into so what we basically want is something that can allow us to create circuits that look like this, right? But just like a nicer front end. So let's now look at the expander. Huh? Yes. But to understand it, so they are using GKR, but they are using the advanced version of GKR, right? So they have already integrated the Libra improvements into it, and they have integrated the Virgo improvements into it. Then I think they use like Orion for their polynomial commitment scheme. Hmm? Which one? Orion.
Orion.
Yeah. Like a polynomial commitment scheme. Okay? How do we do this? How do we do this? How do we do this? How do we do this?
We are using KZG and GKI.
Yes, yeah, using KZG and you're using Vijika. So you saw how like your Adai and your Molai was ridiculous. Like it was mostly just zeros.
Yeah.
And then only a couple places was the one. That's inefficient. So Libra, people that are reading Libra now, when you are done, you're supposed to be able to tell us how can we change our yes. What is it?
I have a question. So what's like when is this going to when are we doing that?
On Friday.
Next Friday. So what are we supposed to like are we going to like implement?
No, you don't implement. The goal is that you have the ideas in your head. And you tell. So what's going to happen is that everybody that is doing. So we'll do paper by paper, right? So every other person that was not in that paper group will be in class, right? Then you present to those people and us. Then my own job and Francis' job is to find where your understanding stops, right? So we'll just ask you questions until we find where your understanding stops. Then once we find it, if your understanding stops before your paper has even like finished, then you know that you're not really understanding anything. And you cannot really like fake it. You can't fake understanding, especially these things. If you have already failed. Like just asking this question, you have already failed. Like no. Like why are you already preparing to and then you don't understand it then. If you are forgetting it, that means that the knowledge is still it's not strong. You can't forget something you understand deeply, regardless of how much you try. Then you didn't really understand it. You can't already start preparing for this. Like it's ridiculous. It's ridiculous.
They said we should be prepared.
Yeah. Like no. There's a difference between like I didn't understand it, right? But then this one is not like you understood it already and then you can't forget. But it's possible that the papers are dense. So it's also possible that as you guys are reading it, you guys will not realize that this is really difficult. I'm expecting such. So, but what you understand it well. That's all. And then we'll check where you stopped in your understanding. And then the tip is that try and get, the papers have ideas in them. Like 1 or 2 ideas. Your goal is to get the idea. That's like the main thing. Not necessarily understand everything line by line. So I was telling them that the better route is just like get the gist first, right? There are some parts of it that might not make sense, but try and get like the gist. What is this paper trying to tell me? What have they innovated on? And then once you get the gist, you now start getting like, okay, how did they do it? You might understand how they did one part, but not understand how they did another part. You go back, try and figure out that part, or you skip it, go and figure out another part. But try and like build like a sketch of the thing first, and then add more details to that sketch, rather than trying to. So it's like trying to build a car. You could start by building the steering wheel, and then the brake pad and everything, or you could build a bicycle or a scooter first, right? Something that kind of like works already. Then from that you build a bicycle. Then from that you build a keke, and then from that you build a car. Rather than just going straight to the car and building like the steering wheel, and then you just don't know what to do again, and you don't have anything that actually like works. So just get a sketch and then just add more stuff on top of it. If not, and it's better to do these things together. Speaking from experience, it's like you need somebody else. You need a couple people, just like.
Can you say that again, please? Say that again, please.
It depends. So you need a couple people because somebody will see something and know instantly what then somebody else might not. And it's this like that's what really like breaks those things. That's what breaks this thing. If not, you might just it's possible to still do it obviously. But it helps when most people that are thinking on the same wavelength are together and doing it. Thinking on the same wavelength, very important. Very important. But yeah, we'll see. So if you have any questions, just ask us. Okay, let's look at expand. Actually, this is it. Yeah. So let's build a Fibonacci circuit. Let me just write code there. So I don't know. Do they have Francis? Do they have crates, or it's still just GitHub? Really? But I want to import it. What's the expander compiler? Is it compiler collection? That's this one. I can't recall. Yeah, expander compiler. What would lock it? Okay.
What does that blocking mean?
It means that somebody else is using that file. That's something else is using the file. And it doesn't want you to change it while it's reading from it, so they lock it. Then when it's now done, it will unlock it. Then you can now use it. But usually that happens when I'm running like an IDE, right? And I'm trying to run on a command line. So the IDE is trying to, let's say, do something with that cargo or terminal. So I'm not allowed. But I think it's my Neo Vim, yeah, concurrency. I think my Neo Vim that must have been stopping things.
Yeah, it sits in VS Code too. So
Yeah.
Is it blocking?
Yeah. So waiting for file lock. Okay. So that's how you import it, right? You just like expander compiler and then this thing, right? So now want to build a circuit. Is it better? Is it better? It's still not good enough. Okay, let me use Rostrover. Good? Okay, let me wait for this guy to load the libraries. Okay. It's too big. Okay. So this is how you get like all the front end related stuff.
I thought front end is front end.
Like web. Web?
Front end is code. I thought front end is like
Web.
visual, yeah. Visual.
No, all these concepts are general, right? That is used in that context. But front end is just there's a system that has a front side and
Backside.
Like a user interface. Like
If I mean to backside, see.
Now you still think of
Can you see? I never say.
oh yeah. Are you ready?
Yes, sir.
So that was a very simple circuit. All the circuit does is that it checks whether you multiply two numbers correctly. Okay? It's just doing more-ish. So it's like you're going to give it three numbers, A, B, and C. And you're claiming that A times B is equal to C. How would you do this in your GKR? You do more, right? Then you put like 0, 1,
Yes.
then okay, so let's see now. So the first thing you do is you declare a circuit, right? So let's say more check circuit
this declare
This
circuit
declare
is
from the front end.
from
Yes.
So that's like a macro for.
Yes. It's for a macro for specifying your circuit inputs.
Yeah.
Okay? So now we have three inputs.
okay, more check.
I just called it more check circuit. Yeah.
Oh.
That's me that called it that. So anything you want to call your circuit, just put it here. So then, let's say A, right?
Yes.
A is a variable.
Variable is a type.
Variable is a type from them. Now the variable is just an AU size. You know, all of you have like the ID on the next layer, right? That's kind of like it. So this now will be like 0 for the first variable. So they are doing what you are doing, but they are making it like. Then you also have a variable again, right, for B. Then you have C, which could be like a public variable. It's the output. It's the thing that you want to expose, for example. Anytime the variable is not going to be technically be exposed. It's going to be like ZK. You know, when you're doing ZK, you're hiding some things. So variable is kind of like, it's hidden, while public variable is like, is exposed.
So, with this automatically, like, version A as 0, B as 1.
Yes.
Automatically.
Yes.
But
Not yet, but yes, yeah.
Can we work with the structure we understand? You know the structure we understand, A the output, B and C and the inputs.
No, this one.
It still works, but yeah, you could do that technically. What you're saying now is that this is what you want, right? A equals B times C. Right?
Yeah, this one is, yeah.
So A is the output, A is the
So what's the difference between public variable and private?
public variable is something that can be exposed. That's like
But it's still a U8. B size.
use size. No, so sorry. All these variables now they'll be replaced eventually with like actual field elements, right?
Okay, field elements.
Yeah. But for now, you're creating like a circuit. Yes. You know how your circuit you create it first before you actually pass in the concrete inputs. That's what we're doing here. So at this point, we don't know what A is, we don't know what B is, we don't know what C is, but we've given them an ID.
So, but you mentioned that variable was like U size.
Yeah, so the ID is represented as a U size.
Okay, it's like an ID.
U size. So like the first one is going to be like ID 0. No. The value is going to be a field. This is just like we're giving an ID to everything. Then the circuit compiler will not like take everything and like create a circuit based on that.
So A is now the output.
So in this case, A is the output, yes. Or the expected output. Or the claimed output. Yes, I am. Okay? So now that we have defined our circuit, I think the next thing we're supposed to do is to implement a light to bright.
No, you can't.
Okay. I think implement define. What's supposed to be here? The config. Give me a second. So this is what we're doing that time. We're trying to make like circuits for ML. That's like any AI. It's take an AI model and then it's converted into a GKR circuit. Then you can kind of like prove inferencing on the AI model. But I'm coming. So implement define.
Why config? Where's config?
Wait, I'm coming. Let me just get it working first. Then, before I explain something that is not even correct. I'm coming. Okay. So you use the config here, but not a generic config. So they have 3 types of fields, right? They have F2, JF2. They have MESN31, and then they have BN254. BN254 is really large. It's like all those ones that you guys were using that time, like BLS. Yeah. Then MESN31 is smaller. It's just like 32, almost 32 bits. So you can represent it with like a U32. Every MESN31 field element can be represented with a U32. Then GF2 I think is now like just binary fields. So also just use like MESN31. Okay. Relax. This is just a trait, right? And the trait will have trait method. So this is the trait method. So this is where you now write like your actual circuit. You write it inside of here. Okay?
So we are binding that trait to this small check circuit.
Yes.
That we have to implement the function that I need.
Yes. So now we can also write in our constraints. So all the constraints are inside this API. Okay? So what do we want to do? We want to add, is it add? No, we want to multiply B and C, right? And the answer is supposed to be equal to A. No, we flip it. Okay? So we'll call this product. Let product equal API the mul. Okay? These all create the mul gates. Then you're now passing the IDs.
Where is API from?
API is coming from here.
So are we trying to override this?
What do you mean override?
Because where we trying to put this API there?
API is from this trait.
Okay, so us defining this define
Yeah.
function now. So
So-
this define function is inside this
Trait, yes.
So when we are writing it, are we trying to override what's creating now?
So trait is like an interface.
Yeah.
Like an interface, same way you understand interface. So when you import an interface, let me use something you understand. When you import an interface now, let's say a particular contract, that means you're using that interface for implementation. So you have to like implement the functions that exist in that interface. So that is what is happening here. So that trait defined now is an interface. And when you do this syntax, like public trait, what is this?
And this is the
Yeah, when you-
interface description.
Okay. So when
Yeah,
you,
continue.
When you do that trait for a particular struct, you're saying that you're constraining that struct to implement what is in that trait, that's that interface. So that's where you do it.
So in the define, right, there's no implementation for this define. So now we have to like implement it for whatever we want to use. So this builder is the thing that adds gates to your circuits. So right now we're adding a more gate. And this more gate is supposed to take in what? Self dot what? Self dot B and self dot. More for more now is just, I think it's just 2. So it's binary up. Okay? So now we have multiplied the 2 of them together, and then we have stored the answer in a new variable called prod. So now this prod is supposed to have the, make sense? Then what we're not supposed to do is we're not supposed to check that this prod is equal to C. Self.a, sorry. So how do we do that? We do API dot assert. So there are different ways to assert. You can assert if something is equal, if it's non-zero, if it's bool, blah, blah, blah. What we're asserting now is that it is equal. Prod and what?
But we are not set K now, so how are we asserting?
That's the point. You are making a circuit. You don't need to set the values before you can make your circuit.
Okay.
So what it should just do that is to just create something that can check if 2 things are equal. But it's to put placeholders for those things. I don't know if that makes sense. Like this will create a circuit that checks if 2 things are equal. But you have not assigned the input layer of that circuit. So right now it's just working with.
Okay. It's still a template.
Yes.
Yeah.
So what it is doing is that it is taking the IDs and it is using that to construct a circuit. So like this one is going to be probably ID 0, right? Then this one will be ID 1 and this one will be ID 2. Then it's now say, okay, I'm going to take ID, whatever is at ID 1 and whatever is at ID 2, I'm going to now put them into a more gate. And that will give me a new output. I'll call down ID, let's say ID 4. No? It doesn't know yet. So is this now going to be ID 4, right? Then I'm now checking that ID 4, whatever is at ID 4 is equal to whatever is at ID 0. So this will basically create your kind of circuit. But now you can see how much like easier it is to do something like this. Because we can just write your computation directly. And then it will do all the combinations for you. So yeah, let's do that. But does this make sense? The template. So now let's write a test. So what you're supposed to do now is you're supposed to create, I'm going to reference this guy. So the first thing you do is you compile your circuit. And your circuit compilation is going to take your actual circuits, which is what the mall check circuits, but you use the default version of the circuit. Then it's also going to take your compile options. Don't worry about that one for now. No, that's default. Sorry.
Very good question.
Yeah,
Think about question.
I'm coming. Okay. Yeah.
So the compile is also like from the front end, yeah?
Yes.
Okay.
Should I remove this thing so that we can see all the imports?
Yeah.
So it will break everything, but then we'll just import them one by one. So now you can see that declare circuits is under. It's not under front end, so it's under like expander compiler, but I think it was re-imported. Then define, then M31, then variable, then root API. What else?
Use those two.
So you can see it doesn't even need front end.
Oh, why is it?
Huh?
Use those two. Those two.
It is also makes sense.
But the compile is okay.
Compile is inside the test, that's why. So now this is our compile. So we'll compile the circuits, which will basically like sort. Right now you're just adding gates randomly, right? You're just adding gates. You're not saying anything about layers.
Yeah.
So what this compile will do is that it will arrange everything into the appropriate layers. So using topological sort. This one you get it from Virgo++. If you read Virgo++, you'll see how this is done. So it's layers. Okay? Now that you have the compile results.
Sorry, one question.
Yeah.
The compile, you said is it doing the whole, what's it called again? Is it doing the DP thing?
Data parallel.
Like is it grouping?
That we don't think so.
Okay.
We don't think so, but we're hoping so. So next thing for us now is to look into how like expander itself works. That's like a code base. So we're reading Virgo++ first. Once we're done with Virgo++, so now I'm going to look into their code base. So because ZKML now has a lot of circuits that are repeated, like ReLU for example, or Matmore. So it does not make sense if they're still treating each one as individual. So we now go in and then we realize that it's still individual. Then we'll see what we'll do after that.
So is Virgo plus tell you
No, Virgo++ is just how this thing works currently. But we need to understand that before we can even look into
So I was thinking that there was the people that talked about that.
data parallel.
Yeah.
Yeah, there are a lot of people that talk about data parallel. But it's not Virgo++. There are more, but I'll find it. I'm really finding it now. Okay, so now that we have the compile results, we're now supposed to do the assignments. Okay, so that's why we're not giving like the actual values. Yes. So let's assignment equal model check. Right?
Yeah.
Why isn't missing 31? So this one is not like concrete. Now what's A? Let's give a random A. No, so we can't know A first, right? Let's know B. What's B?
Yeah.
You said 2, right? I think from. Is it from? Then what's C? So what's A supposed to be? No? So let's say you made a mistake as a prover and you now wrote 57, alright? So that's your assignment. Now what you're supposed to do next is I think you're supposed to generate a witness.
But then I was still trying to get the outcome that I was finding the value to be.
Aren't you trying to?
I'm not trying to
So no, they're trying to check. They're not trying to compute. They're trying to check that a computation was done correctly. Do you get?
I thought circuits were like to compute.
You can use it for computing, but the ZK goal of ZK is to check that a computation was done correctly. So obviously you could do that by computing and then maybe checking outside, right? But you could also like get the answer in and verify it within the circuit. So usually it's like this multiplication ideally should not happen. It's too cheap, don't worry. That one doesn't really make sense. But now we don't yet know how. So like all this like really difficult computation is supposed to happen outside circuit. They are supposed to get the trace, like the A, B, C. Then you now have something inside already that can do like the circuit checking, the computation checking.
This whole stuff is very important. You know, before we don't basically like we just passing the input and the circuit will tell us what the corresponding outputs are until it gets to the final output.
But then you take that and pass everything to the prover, right?
Yes.
You are passing the prover the W0,
Yes.
the output.
So what we are doing here now, it's like we are computing what we give to the prover. Is that what we are doing?
Your entire the prover is going to take this obviously.
This is what the prover will take. So
But it's still doing the regular computation. Like this prod is going to have the actual multiplication answer.
yeah, but we are not supposed to. Okay.
So the only difference is that we're doing this assert here,
Okay.
right?
Yes.
But it's still doing the multiplication internally. But just like you're not asserting if it's equal. So one thing we're asking them, like, is there a way for them to like send just the prod out, right? Rather than like performing an assert. Well, it seems like there's
Okay,
no way
that
to
means-
solve
Sorry,
that right now.
I have some reason kind of similar to this. So is this trait defined now more like us just, let's say if we created a struct like randomly and let's say we have like an init method, right? And in that init method we are just basically something like the way we initialize our multi-linear polynomial, and we had to say, oh, we had to check if the values we were given is kind of like the power of 2 before we created this. Is this sort of doing that? Because this defined trait kind of seems to me like, oh, as I'm initializing or as I'm creating this, defining this circuit, I have to assert if it is like, if that ABC basically is the correct pair. I don't know if you understand what I mean.
Okay, I think I get it now. You know, in our implementation we have the left input, right input, and the output, right? So these are basically the indexes, right? So the output A here represents the output index. It makes sense now.
Prod represents. Wait, so define now. What define does is that this builder, okay. So when they want to generate all the constraints or before compiling, what they'll do is that they'll create an empty builder. That builder is the thing that holds all the constraints that you're putting on your circuit. Okay. So this define is now like for this particular computation that you want to do, add your own constraints to the builder. Okay. So right now we're doing a more computation. So it's going to add a more gate to the builder. And then it's going to add an equal gate to the builder also. Okay. So define is just like it takes a builder and it adds more constraints to that builder. That's what define does.
So this is just like us adding a check to make sure that whatever we are creating is correct. Like whatever circuit we are initializing sort of is correct.
So this is what creates the circuit.
But before creating, it has to assert now.
No. This asset is not like it's actually going to assert here. It's going to create a circuit that can assert.
Oh.
This one is also it's not going to do the multiplication here. It's going to create a circuit that can multiply.
Yeah.
That was what I was talking about.
But it's giving you the IDs, yeah?
This is the same thing with our structs now. That's struct that these gates now. They are our gate struct.
Exactly. It's just a different way of writing that circuit.
Yeah.
It's just a different way. So the IDs is like what your IDs are. So this one now is like your mall gate. And then your mall gate is taking in normally you, yes. So this is the left index. This is the right index.
And you want to make sure that the both of them, if you multiply them, gives you this.
So
Can you also add an add bit here?
yeah, you can add it. So we'll do a more complicated computation, for example. Yeah.
So let's say we do want to like create a circuit that is I could assert we just wanted to do a computation with
And return the output.
Yes, we will not add that last.
I don't know how they will do that in Expander. So until we're gonna look inside.
So this expander is only for you to like create something that you can check.
Right now, that's how all the examples have been. They have it for sure. Because there's no way they can do this assert if they don't actually get the value of prod. So there must be a way to do it, but we don't yet know how to do that.
So expander is like a crate. A crate, right?
Expander compiler collections, yes.
Yes, that helps you to build circuit with Rust. It's like the same thing that Secom and Noah will do, but now with expander you can do those same things now with Rust.
Yes.
That's just what expander does.
But now it's like for GKR. Why we're even teaching is because it's GKR also, yeah. So it's the most relatable. It's
If
the
we
most.
use this expander circuit, are we still going to change our GKR code or
No, they have their own GKR
okay, that one?
implementation. Yes.
So what makes this thing GKR?
No, this is a front end. But then they use a GKR back end.
Okay.
So circuit is front end.
Yes. So like your back end would tell you the type of circuits that it can accept. So that is just like a front end that they will now compile it down to something that is suitable for their GKR backend. And they will now pass it. So you could use this now, right? And compile it down to your own circuit structs.
Yeah.
Because you have all the information there technically. Right? You have the IDs for your left, for your right. So you could create a mall gate, put in a layer with all the appropriate distance.
Sorry, you're confusing me when you're calling this thing front end. I can't relate. Like, when you call it front end, I can't relate to it.
Front end,
You're calling it front end.
your I don't know how best. I don't know what.
So, like, when you understand, is it like,
Relax.
if you're giving this thing
Relax.
to GKR now,
You can't give this like this now.
so
Alright?
that means it's going to compile to something.
Yes, the circuits.
The actual circuit.
Yes. So wait, see now you see this compile results, right? I should be able to do something like I think dbg compile result dot layered circuits. You might not understand the circuit, but it's a circuit.
Wisdom, it's not also a front end.
Yes, it allows you to write circuits that will now be passed to. I think they can allow you to do both gross16 and Plonk. So those are the back ends. But you write the circuit with Secom. Then there's not like a Secom compiler that will compile it down to this form. So gross16 is expecting R1CS, right? So you take that Secom code and they'll compile it down to R1CS. Then it'll pass to the gross16 prover. But Plonk is expecting like Plonkish arithmetization. So you'll take that Secom code and convert it into Plonkish and pass it to the Plonk prover.
So our GKR is expecting our GKR
Circuit.
So this one now compile to that GKR circuit.
Yes.
Our GKR circuit is a struct.
Yes.
So this one will compile to that struct.
This is struct, for example. This is the layered circuit. But it's crazy. But I'm coming.
So you just have to
And 6
Also that
layers.
one.
Yes.
Oh, it's okay.
It's because of the assert. Okay.
What is
These are all the these are all the let's say layouts now or circuits.
Why do we have six circuits? We created just one. Okay, the test.
Which
Is it
test?
the test?
No, it's not the test though. I can remove all of this and it doesn't matter.
Oh.
Wait, can you
Why are these?
I cannot. Until I finish learning Virgo, then I will now come and explain. But it might not be so complicated actually. Let's see. IN0 is probably like input 0, right? IN1 is probably input 1. So this one is like public input. That's probably the A. Yeah? So they stored A in probably in output 0. Then in output 1, they seem to have done like maybe this B times C. Right? So that should be the product. So that's in output 1. So let's say that this is like B times C, expected product. And then, no, this is expected product and this is actually what the circuit got as the product. I'm assuming this now. Now, what is this?
Look like they are doing
This for the equality, I believe.
Looks like they first get a multiplicative identity, a 1 at the end.
Mm-hmm.
Then they are doing times equal to. So like you get the multiplicative identity, keep it down as a variable. Then the B, then like that identity times equal to B, then times equal to C. That's why we have I in 0 times I in 1 times I 1.
Mm-hmm.
So the one there's like the multiplicative.
Yeah, it doesn't affect, right?
Yeah, it doesn't
So
change.
this
now.
is just like B and
So
C,
if it was for add,
and this is A.
yeah, if it was for add, you have 0 as the additive
Should we test?
identity. Yeah, let's see.
wait, is that thing that is there, is it proof?
I'm coming.
You see, what is it?
So what they did now is they multiplied inputs. This will be B, right? Then this will be C. Then this will be A. So somewhere they have to do. Oh, see, they added both of them
Yeah,
to the
together.
same output
Oh,
one.
yes.
So it's kind of like they still summed it. So the output one contains A plus B plus C,
Yeah.
and then this one contains A. But somehow they need to. I think the rest of this is just to do that equality.
That assertion.
Yes. Let me try and remove the assertion. I don't know if it will let me compile, but let me try and remove the assertion. Oh, it does. It doesn't. But it has constraints now. What do you mean? It has constraints. How can I do this? Okay, let's try that. Can't work like that. It just can't work. You have to assert, like, it only works with variables, not concrete values. So there's no way for you to just like say true.
Split the variable too.
So how is it how is it constraining this define to make sure you're asserting?
What do you mean?
You know when you remove the assert, it's not working.
Yes, it's not working.
So like
No, it's not compiling. No, not that it's not
compiling.
compiling. It's saying that there are no constraints on the root
so
circuit.
that means there's somewhere that they are they are ensuring that you have to assert something.
Exactly. You have to add a constraint to the root circuit itself somehow.
Wow.
But it's fine. Let's just continue for now. Okay.
The question is, that trace, that thing that was, is it like the expander circuit moving
No,
circuits?
that's just the circuit representation. Yes.
How is it supposed to represent the one single gate circuit?
It's not just one single. There's still an assert equal there somehow. And equality, like just trying to think about how you would do it. Check if two field elements are equal.
So if you have two gates to more than this,
Yeah, let's add another gate. Let's do both the add and the more. Alright. Wait, but it must be doing something else somehow. Let's see. there's this one here. This does B times C, right? And it puts it in, and then this is the public output. So now where's the?
I don't think it's printed on
I think because we didn't assert,
Push assert level.
that would be ridiculous. Now
Now it's doing more than one.
it has two outputs now.
Yes.
So it's based on what you assert. It seems like maybe to start from the assert layer, then it's now work backwards. So if it doesn't say any assert layer, then it's things that you did not put any constraint because we never saw anything backwards. So that's why it's probably giving us an error when we. But yeah, all these things now are more like implementation details on their end that you cannot really understand until you actually go and look into their code base and see, okay, how are they representing circuits? What does all of these things mean? Okay. So we're doing prod, right? Then we need to do the assignment here. Then I think we can just like generate the witness. Just like I think it's just like the inputs to the circuits. Then once you have the witness, you can now run the circuits. So you do like,
Get to fill.
yeah, the first fill now.
So we were not running the circuits before.
We're just compiling it.
But it
So
was
the running of
running-
circuits like evaluating your circuit.
Yes. It's kind of like, so this is not tell you whether like it was true or false. So you see, called the multiplication of those two things was not equal to like the actual thing. Then we can now do like, you said? Yeah. So what is it supposed to be? One. Makes sense. Let's do something more complicated. Yeah.
So, I understand that this expander now is like a helper for you to like construct your circuit.
A circuit. Yeah.
Yeah.
Their own.
To construct the circuit, right? Now, when you construct that circuit, you can now like use that circuit structure in your GPR.
Pro system. Yes.
You understand? So now that means this expander, the circuit is returning, like when you construct a circuit, you're going to get like a template.
Okay.
You understand? For instance, if we come back to what we did, our own circuit template is the struct of our circuit, which is what our GPR accepts, right? So this circuit now, when you have constructed your circuit, what does it return? Like,
It's not a struct too.
okay,
So let me print out that one. I think it
I
was,
don't know, is there a way we can like just see the structure, like where it's defined, so that
wait, let us first get the name, then we'll see. So I think it's just called circuits, alright? So let's now open. And we're looking for like struct circuits. I think it's this one. Now let's expand. So this is their circuits.
okay, so since this is what this stuff is returning, that means if we want our
feel like-
G,
Yeah, continue.
eh?
Continue.
So if we want our GPR to work with this circuit, we can construct our own circuit struct to match this same thing. So automatically, if we
do
use
that.
this circuit like we use this guy.
You can prove it with your own GKR.
So we can prove it with our own GKR.
Relax first, wait. Yes, in theory, yes. So wait, this is what we did with Secom GKR, right? So Secom R1CS, we already had our GKR circuits. So what we did was that we converted Secom's output. We wrote a compiler for like Secom that now converts to our own GKR circuit structure. So we're not able to prove Secom with GKR.
Okay, so you wrote it to give that
My own, yeah.
So can we do this to do the same?
So wait, yeah, that's what I guess too. So now, yes, in theory, if you can, let's say, depending on why you want to do it. You know, you could. There are two ways, right? What you could do is first of all, you could do like a compiler that takes this circuit and converts it to your own type of circuit, or you could modify your GKR to work directly with this circuit.
We use this one to get our
Okay. Now, in order to be able to do that, in order to be able to do any, you need to fully understand this, right? That's where the problem comes. So now, I don't know. I feel like these guys are using Virgo++. It's not regular GKR. It's over optimized GKR, and it's possible that you might work with multiple layers at once. You know, right now GKR, like this layer works with the next layer. In Virgo++, this layer can work with any other layer under it. Do you get? So you can take your inputs from here, and you can take your second input from layer 52, and you'll still link up like that. So now, if they have already compiled their circuit so that it is now layered in that sense, then your GKR can still work, which the name layered circuit kind of hints at. So you need to like actually look into that and make sure that's the case. There's nobody. But it will be crazy. But we are learning it right now. Yeah, that's how we realize that if we had given it would have been crazy. But makes sense. So if we're still around, it doesn't even matter. We could always just like host like a call or something, and then or make a YouTube video. There's zero resource on Virgo++. Zero. No, normally there are resources here and there. This one there's zero.
Is it like a prime?
Is it? No. No. Like when I was, where is it? I think this is it, right? No, this is not it. No, that's not it. It is it. There is no resource that exists on the internet outside this paper and one implementation of it. No, there are a couple implementations of it. This one and then expander. Zero. No YouTube video, no blog, no resource, no nothing. I feel like the number of people that actually understand this thing is just a handful in the entire world.
That this thing was given before.
Huh? Abi? Abi? But it's that shows you that we are still like really close to the edge. Like no resource, meaning that nobody understood it well enough and cared enough about like to write about it.
People that implemented Expander, they didn't write anything about it.
No. But the people that so this okay, no, it's not even here. Yeah. But yeah. The point is there's still a lot of money to be made. Just because of if you understand stuff like this, you don't have competition. I don't know, like you just do not have competition. Because do you know who would sit down and then go and like try and understand? You just don't have competition. And pay flips depending on competition. Like if there's a role that has a lot of people that know it, now it's the employees that are competing, right? But then there's a flip when you now have more employers than people that know it. The pay is inverse. Like they're not competing for you, so it's like this is where we should be pushing towards, not pushing towards things that everybody already kind of like knows. It's just like
So if you were to implement this now, let's say you read it, if you were to-
that's already crazy. Yeah.
So like what would be the next step?
You reach out now.
How do you reach out to them?
You want to Twitter, Telegram, everything. Everybody's everywhere.
There's no Telegram on the. Or they not even Telegram.
You'll find out. Don't worry, you'll find. When? Me and Francis like 1 year now. 1 year, seriously. Before I met Francis, I was just like, we're just reading, like, not papers, not anything, just we know the concepts. Then we know maybe what fields and all those things. But then I just quit my job, my blockchain protocol engineering job. I left that one. Then we just focused for like that was like last year, January. So what we are doing with you guys now is what we did. Like we just started everything. And then we're not figuring out, oh, we did GKR wrong grade, we could have done it this way. And then, so it's not like, that's what we're now like telling you guys so that you guys don't have to like go through that. Some people are closer than they think. Some people are very far. Like in this group. Some people are closer than they think. Some people are very far. And some people are like in the middle. So it depends on effort. It all depends on effort. But there are some people that I know that okay, if they continue in the next, let's say, 2-3 months, we'll all be working together, kind of. We'll all be working together, like learning new papers and stuff. But I know them. I know them. They might not know themselves. Some might know themselves, but I know them. But me, I'm using what meets the eye right now. So there's always a chance of being wrong, right? That's on the other person to prove that. That's on the other person to prove that.
Are you saying where you are?
But what does not do that? But what does not do that can never be good. What does not do that?
That must be rough, exactly.
A percent of the class that I think I won't say. But just know that anybody or any subset of people that want to kind of like take this to the next level, like you have access to me and Francis. You have access. That's like if you are really serious and you want to take it, you have full undivided access. So it's now like it's up to and also based on obviously factors. People want to make money, right? So there'll be distractions here and there. So it's just like if you are serious, you can get to like Virgo plus. You said? What do you say?
People want to make money though with the structure, yeah. That's I said there'll be only half here and there.
Yeah, exactly. Just so that before you can make serious money, you have to be seriously good. And before you can be seriously good, it takes a lot of like sustained efforts. But if you cross that threshold point, it's like you can be coming out and going into the job market and start over your life because you know that there will always be. But yeah, let's continue. Makes sense?
Yeah.
Now let's do something more complicated. Let's make do you know dot product? Let's do dot product.
Dot product.
Yes.
That's
Yes. Like dot product element wise then you sum, yes.
So,
So let's say we wanted to do like five values, right? So let's say 1, 2, 3, 4, 5. Then B was supposed to be let's say 6, 7, 8, 9, 10, right? Then the dot product is supposed to be first of all we'll do AB, right? Elements wise. That'll be what? 6. Then the sum.
130.
It was faster. Sum equals to 1. Is it 130 or 150? 130. Yes. So we will have a circuit that takes in what? A, B, and sum. Okay? Should I just maybe I should just yeah, so we'll do that. Let me use another one. Yeah, there'll still be IDs, but now a vec of IDs. Cool? So like dot product circuits.
So these are another type present.
Huh?
These are another type present.
Yeah, these are another circuits. No, it's also creating it. What do you mean? This dot
Like, I mean, it's another like.
No, it's
circuit
we.
present.
It's we that do. This one too is us.
Oh.
The only thing that we bring in is declare
Is it
circuit.
possible for us to just move that guy out and just bring
Which guy out?
the all chairs
Yeah.
and that's
That object.
objects.
Yeah.
Just take it out and just bring the object instead of us having the objects declared inside of the.
Like write it as a struct. Like are you saying struct more? This is what you're saying. And then pass it in.
yes.
No. So the reason why is that let's see, let's try. Right? There's no harm in trying.
You can just copy that struct there now, like from that declare, just copy it, paste it out there as struct.
Yeah, I know. I don't want to copy it. If I'm doing the other one, it will be like. So one problem that we're facing already is the fact that let me use variable. But even still, right? There's an error here. I'm coming. Let me hide this one. So it's because of the way the macro works. So because I've seen how the macro looks like, that's how I know that it's not possible. But let me show you guys what the macro looks like. Who has experience with macros? Okay. So it's not like that entire model circuit thing that you put inside, right? It's going to be this line here. Okay? So it's have the struct name, then followed by a curly braces, right? Then it's now have a field name, that's the first one, that will be A. Then a field type, that will be variable or public variable. Then now see this star, meaning that it can have many. So many field name type, field name type, field name type, right? And then at the end of the day, it's not going to have like a closing bracket. Okay? So it's going to take this thing, and then it's not going to use it to create. So this is what the macro will now create for you. So it's creating the struct for you, like what you wanted to do. So it's going to create a pub struct. It's writing this now in your code. And then struct name, whatever that struct name was. In our case, more a template generator, yes. That's what macros do, yeah. Then it's now going to put pub and all the field names and their field types. Make sense? That's the struct. But now the real reason why they created this is to implement a particular trait automatically for you. So that trait is called dump load two variables for struct name. So now they are helping you implement that trait for all your circuits without you having to do it by hand. That's why they created this macro. So unless you can find a way to somehow still give the correct information, you can't just pass, like declare like that, because to it now it won't see in this line now it won't see this struct type structure. So that's why.
That means macro they don't like point to a value, then anything that is specified in that macro must be in that same order and structure. It's not like, normally if you have in like normal programming,
Yeah.
that more check circuit
Mhm.
is the same as you declaring it inside that circuit
Mhm.
instead. It just
It's
points
not value.
to-
Yeah, yeah. It's not value.
But for macro,
Yeah.
the way it is defined is the same way you have to pass it in.
Yeah. So macros are like they take source codes
Yeah.
and they spit out source code. That's what there's procedural macros. That's like superpower. It's like crazy. All those things that you see like derive. Have you seen? You use it a lot now. Like hashtag derive, clone. This is called a procedural macro. So it will take whatever source code is under it.
Yeah.
It will pass it to a function at compile time. Then that function would manipulate the symbols and create new things. So it's like it's taking source code and it's spitting out new source code. So in this case now to implement clone for whatever struct it is. So Golang, where's my dev? Yeah, I don't know. But I know Zig has it, eh? I've looked at it before. And I don't just look shallow. Trying to like really understand it. Then but if I don't know, I'll tell you I don't know. So it's just like it's just knowing what you know, knowing what you don't know.
So there's no convention like the name must end with circuit.
No. You saw the struct name, just the struct name. They didn't really like I just use dot product. So now what is A? A 5 elements, right?
Yeah.
5 IDs. Make sense?
Yeah.
So variable 5. Variable 5. Variable or public variable. Yeah. Huh? They're IDs. Like you're trying to create a circuit template. You don't even know what the concrete values are going to be. But then you kind of like have like an ID to point into where in the array should I take what from. Like CA now, I'm assuming that maybe when you do the witness solving, right, you'll get an array. This array is going to have A, the value for A at index 0, the value for B at index 1, and the value for C at index 2, right? So now you're already giving like A as what, 0? No, B as what, 1, and C as 2. So what it's to do that it's not going to the input when it's actually time to execute. It's going to the input, that's the assignment, and to say, okay, what is that index? 1. It's the same way your circuit works, where your input gates, your input layer, the layer before your input, is specifying the IDs to take values from your input. They're exactly the same thing.
So this
See,
is implicit in yours.
yes, like the IDs are created. I don't know why I cannot open variable. Let me open the compiler. Variable. So they mix Go and Rust in here. Okay, let's should have variable. So see variable. Just an ID. Yeah. You just use size. Finito. There's no public variable. Public variable is from the macro. Like the macro, let me show you. I was looking for public variable and I spent hours just looking for public variable. I was like, how is this even compiling? But here, if you see declare circuit load from, or let me see. So see the type. So it's just a macro thing. That type does not actually exist anywhere. But in the macro, they're like they just type it there. Because inside the macro this thing, you can just write rubbish. It doesn't have to be like valid Rust anymore. Anything between the macros doesn't have to be valid Rust. As long as the macro, because the macro will just take whatever is in there and give you code that will replace. So if the thing the macro now returns is not valid Rust, that's when the compiler will complain. But as long as the thing that's inside is valid Rust, is what the macro wants, and it can want anything, then it's fine.
So the reason why this, what difference in a variable and public variable is that one is stored in the vars and one is stored in the public vars.
Exactly. So that public is just to tell this guy where to put the values in. By the end of the day, they're all just variables. They're all just IDs. So public variable is just a variable that is stored in public vars vector. Finish. So by the time it's done, they're going to remove that like public. I think we should be able to see that actually. So yeah, they say if the type is variable, return type T. And if the type is public variable, also return type T. So public variable and variable have the same type.
Yeah.
But that public is just to allow you putting inside a public vector. That's all. So that one is just like macro specific. Make sense?
Yeah.
So now let's write the define for this circuit. Now we want to do dot product, right? So what do we want to take each one and multiply each variable? Yes, elements y. So we can do self.a, right? Dot eta dot zip self.b dot eta, right? Then the map, we should now have like the a and the b, right? These are basically just what? IDs. Then what we do is now do API dot more AI BI, and then we now get like the results, right? So they'll collect. No, we cannot just do eta dot sum. So let AB equal this, right? So this one over here. We'll do it by hand, okay? Just to make things clearer. So now what we have here in this AB is basically the new variable IDs for all the element-wise products.
Yeah.
Now we need to now take this and add everything together.
So
We can do fold.
Why couldn't we call the item or something?
They're not
like values.
Fold.
You need to use API dot add, right? But you could use fold. You could use fold for sure. But let's just do how do we do this? What's the best way to do this? Okay, let me just try it. Let's sum equal variable dollar default. Then okay. Yeah, we can use reduce. We should also use reduce. Reduce will be better. I'm coming. Let me try reduce. So AB dot.
So
It starts from the first one, right? The reduce. So reduce takes in two things, right? I think the accumulator and the current. So what we need to do is like we need to return API dot. So instead of eta, I'll do into eta. API dot add. So we want to add the accumulator, right? And the current. So that's going to give us a new, and then it goes. So this is supposed to be the sum. All these things.
I'm trying to remember, this accumulator, is this 0 or the first value?
First value for reduce, but for fold it can be whatever you pass it in. So that's the sum. Then what we need to do is now like assert that what?
The sum is equal to self.
This is your circuit. Into eta would like takes ownership. But if I use eta, what would have happened is this accumulator is a reference. But API.add does not return a reference. It returns a full variable. So there's not like an inconsistency because API.add is supposed to now be the new accumulator. But then accumulator is saying that I'm a reference. So
How's the reference?
there'll be a type mismatch. You can't, which one?
Can't you,
API.add is not returning a reference, it's returning variable. Okay?
What does it take?
Like the ACC.
So exactly like ACC, transfer service control.
You can. No, so API.add, they didn't even put it here.
It does not take.
No, it can take a reference in terms of like the input, but it does not return a reference. It's going to return variable.
Okay.
But now whatever is returned here is supposed to be the new accumulator. But then when we got the first accumulator, it was a reference. So that's already fixed the type of accumulator to be a reference variable. And then you're now saying that I'm giving you a new accumulator that is variable. So Ross is like, why are you giving me two different types for the same variable? So that's why I now made this like into iter. So that the first thing is a variable and it returns a variable. Everything is fine.
But if
We're
you're
using
using
the reference, like the reference accumulator current.
Yeah, add is the input to add is not the problem.
I mean from here.
from with dot reduce, that's
Here,
Yes.
I doubt, but let's check. So do what here? This is not like a value. This is just like it's specifying what the signature is. Yeah. Which
so into it that is like saying dot into.
no, it's still iter, but it's taking ownership. So it doesn't need to take it. It doesn't need to give a reference. It's taking the values.
But this is because we are not using like AB after.
Yeah. So like this AB now is where we're getting the values from, right?
Yeah.
And we're not doing into iter. So it's not saying that okay, I'm consuming every value in AB. So that means that this AB will be destroyed once I'm done. So I'm not borrowing the value, I'm taking it. So now if I call AB underneath, it can't work anymore. But if I wanted to use AB in the future, then I need to make this what? Iter.
So, and then you can.
Then I cannot use AB in the future. But now if I was in this context and I wanted to use AB, but I needed to use it as a variable, then I would do like cloned. You get? So I could do like dot iter, then dot cloned. That would do what we have done. But now it's duplicating AB, which we don't need to do here. That's just wasting memory, yeah.
So what if we leave it as beta and then what forms of API or add we add like the
Up and
can
side.
you return the borrowed value?
You can depend on where the borrow,
Yeah.
borrow is like this is the address to somebody.
Yeah, exactly.
Now if you return an address, it means that that person must be there, right? And it must stay there as long as this address exists. But now the problem is that this is a closure. Once API.add returns the person, right? So this is the home. Then you're now returning a reference to the home. So the home is here. But once we're done with this closure, the home gets destroyed. But then you're returning an address. So it's like it's problematic. Ross basically said that like temporary I'm coming. So you're saying like something like this, right?
Yeah.
It just builds, that'll be crazy.
Let's see. Yeah.
So you're saying temporary value created here. And then you're not trying to return it. So it's like you created the home, you're returning an address to it, but then the home is going to get destroyed instantly. Exactly, after every iteration. So it doesn't work. But I wonder why this guy didn't complain.
It happens now.
Bruh.
It's like technically correct.
This is not my ID.
Like it follows
This is not my ID, this is my ID.
at the end of the day.
Okay. So what are we doing? What did we change? We changed this. And then we changed makes sense? Okay. Now we can just do the same thing. right? Well, let's see what this circuit looks like. Now let's use this other one. I don't know if I'm allowed to do this, I guess. Wow. The shots. So this is more like it feels this. I don't get this. This is dot, right?
So yeah, it's multiplying like 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 3.
Okay, and it's summing everything in one variable. So it has already done everything, kind of. That's crazy. It has done everything. So it just compares this two, and I'm assuming that all of this is. I don't know, but I'm assuming that all of that is like compared. So that entire dot product thing was just. It's just this. This is the circuit. So then we can now do our assignment, right? So the assignments. MP1. A is what? Sorry. Oh no.
Yellow shortcut.
So this one was 1, right? Then this was what?
6, 7, 8, 9.
Yeah, so we'll just ignore, we'll make it fail first. Cause I don't actually know if this will work.
Or eyewitness.
130. Okay, 130.
The answer is a fail. Makes sense?
So can you go back to the eyewitness?
Yeah?
The eyewitness.
Eyewitness. Oh, witness. I can print this out too. So it just like flat. It just puts all the results in a flat array. All the inputs, in a flat. But the IDs already tells it where to go and pick the appropriate value from. Make sense? So yeah, let's try 130. It might not work. If it doesn't work, then our dot product is faulty.
True, no.
It works. So you see how easy it is to kind of like write dot product. It's almost like I'm writing the actual dot product computation.
And that's why I'm surprised why they call it Frontends. Because it's almost like you are writing the same
No,
method.
if you write dot product for your GKR circuit. No, it's doable now. It's easy. Actually,
So write dot product.
for your GKR circuits.
It's writable.
Yeah, it's
It's
doable.
just to build the circuit for
But
itself.
it's easier to do this, right?
Yeah.
I was thinking when I heard Frontend, I was thinking maybe there's an input.
No. No. So like, if you want to do it with yours, right? You need a MOL gate. Is it a MOL gate? Yeah, you need a MOL gate.
You also need
MOL that will take what? 2 inputs, right? From both arrays. So let's imagine that this one is index 0 and this one is index 6. No? Sorry. Your first array will be what? 0, 1, 2, 3, 4. Alright? Then the second one will be
5, 6, 7, 8, 9.
exactly, right? So you're going to do mul
0, 6.
0, 5.
Then now output it in 0.
Yeah, you can output it in 0. So like we're assuming like more out, then left, then right.
Right, yeah.
And then same thing for add. Out, then left, then right. So you do this, right?
Yeah.
Then what else? You do the same thing, right?
There's 1, 6. 0 and 1, 1, 6. 2, 2, 7.
2, 3, 7.
2, 2,
Yeah,
2, 2, 7.
Oh, sorry, 2,
3, 3, 8. 4, 4, 9.
4, 9.
They will now put the add.
That's all for this layer, right? Then you now take add for all of them. But that means your add only works 2, 2, right?
Yeah.
So there's a problem. There's a problem.
You can actually add them 2, 2, 2, 2, 2. Then
Yeah, but it's not enough yet. Let's continue
For
first.
the
Yeah.
5.
Yeah, exactly. So add what? 0 and
And
Add-
you can do it on like
one can move to the next. Yeah.
you have a copy gate. There are gates that can copy. But you can add extra. Just wait, we'll do it. So 0,
you can make it
That would be
0 and 1, right? No, 0 to 0, 1, right?
Yeah.
Yes.
Then
Add
1,
Then
2 and 3,
1
right?
to 2.
yeah, 1, 2, 3.
Yes.
Right?
Yeah.
Yes.
Now what is this?
You can add 0 now.
Yes. So you can add a 0, but how will you do that too? You can do like
You
mul.
basically make the polynomial for that layer like
Even.
sorry, not polynomial, sorry. You can add like one other zeros to that layer.
Which
You can make sure
0?
that the gate is even. So
You
if
can-
the gate that
Gate
is
is
coming
odd,
in
you
is
just
odd,
add 0,
you add
pad
0
to
to
0.
pad it. You pad it with 0.
Wait, you can still do it on the input layer. Imagine you now put like another input 0 here, right? So now on this place you can put like mul. This will now be index what? Sorry, this 0 1 2. That's like this is index 10, but index 10 has a 0, or it's supposed to be a 0 when you actually like pass in the input, right? So index 10 is supposed to have a 0. You know this from how you define it. So what you could just do is that 5 will output 10 times 10, right? So you just 0 times 0. So that means this gate should output a 0. Then you can now use that to help you add 4, 5. But it should output 2, right? 4, 5. So that now gives you like that last gate. You still have an issue. Exactly. That was, yeah?
Okay. You said more 5, 10, 10.
So 10 is supposed to be the ID for 0 in the input layer.
So technically,
So I'm thinking, okay.
the input layer should be a power of 2
Exactly.
to solve the old
Exactly.
linear. And then we'll pad it with zeros.
Exactly. Makes sense?
Yeah.
So this is how you would have done it. But then if you had like a good circuit builder, you can just do it like this.
So one will have to
You can build this yourself. For the ambitious amongst you, you can write a new front end for your GKL prover. Make sense?
a new front end.
Yeah. That's it.
This implementation.
Like this kind of implementation.
So like when something.
That's for those that already understand this front end already.
No, not this front end. Not this particular. Wait, not. You're not using expander. Your own GKR implementation.
Like I've not understood this one.
You don't need to understand this one.
Wait.
Wait,
Yeah.
Okay.
wait. You know, we have a way of creating circuits already,
Yes.
but we can see how cumbersome it is, right? So what we can do is that we can create another thing on top of our circuit. The output of that thing is your regular circuit structure, but you're going to create something that will make it easier to create that your circuit structure. So you can do something like this.
Okay, wait. No, now you.
So you're saying that
Now you know those kinds of things.
I'm saying,
like
Okay,
create
you're
something
saying-
like expander.
Not kind of, but not really. Wait, something that can build your circuit for you easier.
So when you call it, it will do all the.
It's
Oh,
a,
yeah.
yeah.
I have VM on my mind.
Yeah.
So
VM more important. VM more important.
So wisdom, like, can you scroll down? That thing just flew over my head. Down.
Oh, I deleted it.
Oh, you did it.
This one, right?
That yeah, that last one. You know what I mean? Dot products. It's not supposed to be first, second, and third. Like the first array dot, second array dot, last array.
Mm-hmm.
Why do you put the 10 outside?
So at the end of the day, you create a circuit. That circuit will have a flat input. Okay? So your A array will be the first 5 elements in that input.
Yeah.
Then your B array will be the next 5 elements in that input. Now we're now putting a 0 at the end. Okay? So let's say you wanted to do dot of what we did before, right? That was 1, 2, 3, 4, 5, right? And then 6, 7, 8, 9. Was it 10? Yeah, that was 10. But then you now put 0 here. Okay?
That's the array now.
So this is the input, yes. So now if the circuit is seen index 0, it's going to pull 1 from that, right? And if it's in index 5, it's going to pull 6 from that, which is what we did here, right? 0 and 5.
Yeah.
So that's 1, 6, 1, 5. Is it 1, 5 or 1, 6? Yeah, 1, 6, right? And it's going to multiply the two of them together to give you 6. And then it's going to output that for the next layer. Yeah. But we're like, there was a problem with this, right? Because of, we could do the first 2 for this one, right? And we could do the next 2 for this. But then, this one was the only thing that was remaining. So, we could not, like, create an add gate. Because there was no right input. So, we need to create an artificial right input that's just 0. So, you just, like, take whatever is at index 10 as your left input.
I'm curious.
Like for these small.
0 times 0 is 0 now.
Okay, it's going to be 0.
No, 10 is 0. So it's like we're passing 0 times 0 to get 0. So that's like, this gate will output 0.
So
Yeah.
I'm like, why do you do that? Because if you are saying everything is dot close, that will not really be dot close. Like you are saying this array dot, this array.
Oh yeah, wait. Complete the circuit for me.
No, I'm not saying.
No, wait, no. Come, wait.
What am
Wait. Calm down. Let me show you understand. Let me show you understand the problem. Oh yeah. This dot product, are we?
Yes, so I've done
Okay.
it.
No.
No, it's not
Yeah,
complete.
but dot
Is it complete?
complete.
Oh yeah. We have done the element wise.
multiplication.
That's all of this, right?
Yes.
We need to now sum everything together, right?
Mhm.
Oh yeah. Let's start summing. So we're supposed to sum this and this, right?
Yeah.
Is that what we did here?
Yes. Says 0 and 5, right?
Yeah, 0.
Okay.
The output is 0, right?
0 and 1.
0 and 1. Cool.
Then the next
So this
one.
2. Now the next one is what? 2 and 3, right?
Yes.
Now
So
this
you
one,
need
Nico.
that.
Supposed to be 2. Okay.
So what me I'm thinking in my mind is for that array, right? Let's go and add another index. So something like
Which array?
the 2 arrays at the top. So it's not be 0, 1, 2, 3, 4, and let's say 10.
Inside here?
Yeah, yeah, 10. 10. Then the second array it will be 5, 6, 7, 8, 9, and 11. Then so that means that our last input.
Last, you
our
need
last
2 more
input
inputs,
will
right?
be 10 times 11. Index 10 times index 11, which will give us 0.
Hopefully, if you put 0, yeah, you put 0. Yeah, assuming 10 and 11 is 0, 0.
So
Mhm.
definitely to give us 0, which will now complete the add that we need in the next step. That makes sense as a dot product. That is, you are multiplying 2 arrays.
It's still the same thing.
I'm just like, that's what I'm saying there.
It's still the same thing.
Like,
Yeah, just adding 0 somehow.
Fine.
but you're still doing dot product of
To
the first
No, that's the thing. We're doing dot product
of
of
the-
three arrays now.
mm-mm.
Now.
we are padding.
So the thing now, don't. It's just like the goal is to check your competition, right? So whatever makes it work, it's fine. You are still doing your dot product. Don't make you sleep.
It's just a sanitary.
But-
Which one is that? You did it on purpose. You did it on purpose. You did it on purpose.
But cool. It is just a way to introduce zero to it. Yes. You are introducing it also, right? By putting 10 and 11, and then you're assuming that those should be zero. You also introduce zero. It's just where you introduce zero. You must still do your, yeah, you must get the answer of your initial dot product.
That makes sense.
So, what you were saying then, you should have like, maybe like a function that it only takes the input, then it builds out using those components,
She wants to do that too.
That's what she did for make it actually.
Eh.
Like she doesn't have to take it.
So you should be able to write something like this to construct your circle. So I think we're good.
So this is
See,
the expander.
don't allow this guy ask you something again.
My God.
Then you can also do like things like Fibonacci and all those.
What you said was that we're going to do Fibonacci.
Yes, wisdom.
I love the
That
Fibonacci.
Fibonacci test that we've not still gotten into.
Which one?
There's one Fibonacci.
No, we explained it the next.
Yeah,
We explained it at some point that you cannot just that we're wrong in assuming that. Yeah, it has to be within.
But so that's the end.
What do you mean?
Like, there's no way you can make it work for an arbitrary, like, outside the field.
We're confusing something there. What Fibonacci this thing now? Isn't it that you had a trace, right? All the Fibonacci values.
Sorry? Okay. Come again, sorry.
So like you had what? Let's say what does it start with? 0 or 1 1?
0.
Right?
8.
I'll stop here, right? So then what I wanted to do was I wanted to check whether this sequence was correct.
Yeah.
Right? So we converted each of this into like a polynomial, right? Not each of this, the entire thing into a polynomial. Okay? So f of we represented the entire trace as a polynomial f of x. Now if you evaluate f of x at 0, you're going to get what? 0. F of x at 4, you're going to get 3. Okay? So now this is a polynomial. So we want to check whether this thing encodes Fibonacci.
Okay, so to get the f of x, we basically like interpolated as those. Okay, that makes sense.
I'm not done, Sha. So it's not like you now want to get a thing that can check the polynomial, right? So you need to do f of what? F of x plus 2, right? Yeah. Yeah.
To give you a 0 polynomial.
So this is supposed to be a 0 polynomial. It's supposed to evaluate to 0 for valid x values, right?
Yeah.
So if we do C of, that's something like 3, right?
Mhm.
That's going to supposed to be 0, right? Because that will be f of what? 5
Five
minus f of 4 minus f of 3, right? And f of 5 is what?
5,
F of 4 is what?
3, 2,
5 minus 3 minus 2 is what?
0.
Does it make sense?
So this C of X, so was it like gotten from somewhere, or you just have to like find the pattern?
No, so you evaluate f of x at x plus 2. You get? So let's say f of x was 2x. If you evaluate f of x at x plus 2, that's now going to be 2 into x plus 2. Alright, this is going to be 2x plus 4. So that's how you get this one. Then you also do the same thing and you do the same thing. And then when you now like collect all the like terms, that's going to be your C of x.
Yeah, I'm saying that why do you think of doing X plus F of X plus 2 then F
Because
of
this
X
is
plus 2?
Fibonacci.
Okay, that's like
This is the thing that checks that you did a Fibonacci step correctly.
yeah.
Taking 3 Fibonacci numbers. Make sense? So now this is where we now made a mistake. This thing I was like, this thing now should be holds for all values of x, but that's not correct. It only holds for values of x in this range. Yes. So it means that, I remember now, I think you guys now know KZG. So that means that, or you know quotienting. That means that if it's supposed to be a root, so that means all those values of x, wherever you can evaluate a polynomial at, I'll give you 0 is a root of that polynomial. And you're supposed to be able to divide a polynomial by its root without any remainder. So that means that C of x is divisible by x minus, so where do we start from? X0, right? X0 is supposed 0, if I write C of at 0, that works, right?
Yeah.
So it's supposed to be divisible by x minus 0, x minus 1, x minus 2, x minus 3, x minus 4. I think it's still x minus 4, right? Because that's the only one that has 2 extra in front. Because whatever you do what?
Okay, yeah.
X plus 2, right? So 4 plus 2 is what? 6. And then 4 plus 1 is 5. And then this one is 4. That's all within the trace. But then you cannot just do x, you cannot do 5, right? Because that will be 5 plus 2, which is 7, which is now outside. So those ones, you need to check it as like boundary constraints. Okay? So you check that one separately. But now for this one, all of this should divide C of x without a remainder. So there's not going to be a Q of x as a result. So all you need to do now is check that left side is equal to right side using Schwarzschild lemma. So you just pick a random, now you can pick a random x in the entire field, right? And then if you evaluate the left side, it should be equal to the right side. Because the two polynomials are supposed to be the same. Does it make sense? This entire cx over is supposed to be the same thing as q of x.
It's supposed to be
Yes.
It's like 9 it's like 27 divided by 9 is supposed to be equal to 3, right?
but we said we divide everything.
Q of x
Okay,
is the
Q of X is
quotient.
the quotient.
Yeah, so just
C of X. What is it?
no, C of x is a polynomial that gives 0 when you evaluate it at 0, 1, 2, 3, and 4. But you can also evaluate at any other thing and it will not give you 0.
So it's another C of X.
This is the polynomial. So the C of x polynomial is gotten from the f of x polynomial. So you get this f of x plus 2, which will be a polynomial. You get this other one to also be a polynomial. And you get this one to also be a polynomial. So when you now collect like terms, then you get the final C of x polynomial. I said, like, imagine if f of x was 2x, right? Then you evaluate this at x plus 2, so you get 2x plus 4. So you do the same thing for x plus 1 and x. Then you just merge everything. So you get a new polynomial for C of x. Which is, yeah? No, it's not 0. It's only 0 within those values. which is why it's safe to divide x minus those values. And that should give you a quotient without a remainder. Make sense?
Yeah, so why did you can't add 5 and 6?
Because of, if you put 5 now, then it will be 7. Right?
Well, we are the one that defined that this is where our arm is.
Maybe 5 there to be 7. So it will be f of 7.
Yeah.
Okay.
Which will be problematic because we've gone out of where Fibonacci holds. This thing could just be one random number. So it's like, so you check the boundary condition. So normally the way I read this question is not how it's actually written. Like how it's actually written, like c of x is equal to f of x minus 2 minus f of x minus 1 minus f of x. That way it now flips it. It's this first two that you cannot use, right? But you can use anything under. So now you can now check that the prover started with the two Fibonacci numbers that you were supposed to start with, which is like 0 and 1. Does that make sense? Relax. So I'm saying that, does it make sense that you cannot use 0 and 1? If you do C of 0, what would that be?
Minus 2.
If you do C of 1, it will be minus 1, right? But if you do C of 2, that will now be f of 0, right? Then minus f of 1, right? Then minus f of... But this is wrong. I'm coming.
Where is f of x minus? F of x minus f of x minus 1 minus f of x.
Minus 2. Yeah. So the first one can start with C of what? 2, right? That's f of 2.
2 minus f of 1 minus f of 0.
Makes sense, right?
Yes.
But now, so we'll be able to prove that all these other ones are correct using this same algorithm, but it will be different now, right? It's now be C divided by what? 2, right? That's where we started from. Right? But then we have not checked 0 and 1. Okay? We need to check that. So this is our constraint. We need to check that this holds. But we also need to check that f of 0 is equal to 0 and f of 1 is equal to 1. Right? We need to make sure that that is actually the case. So I think you can use another constraint for that. That's like, it's like KZG. This is basically quotient, where you can just do like f of x minus 0, right, should be divisible by what? So this 0 is like the v. So you know, if you want to check that f of x is equal to v, what you can do is that you can say f of x minus v should be divisible by x minus something, maybe r. Sorry, you want to check that f of r or f of a, right? Then it should be divisible by x minus a. This is how you would check. So we're saying that f of 0 is supposed to be divisible, is supposed to be equal to 0, right? So that means that, so this one now is like, is a root-ish. Sorry. No, you know, I need to like evaluate at 0. I need to like give you 0 is a root. But now it's like, no, sorry. A is equal to 0, right? And v is supposed to be equal to 0 for the first one. Then for the second one, a is equal to what? 1. And v is supposed to be equal to 1. So you can check both of them with like f of x minus, for the first one now, 0, right? Then all over x minus 0, which is just x, right? And for the second one, it will be f of what? X minus 1 should be divisible by, without remainder. You get?
It's supposed to be f of 1 minus 1.
No, f of x.
F of x.
This,
Then like, what actually means? Okay.
this is the polynomial.
That's the polynomial.
Yeah, so you're subtracting 1 so that x minus 1 is a root.
Of, okay.
No, x minus 1 is not a root naturally of f of x. So we need to subtract 1 so that it's now a root. You find a polynomial that when you evaluate at 1, it gives you 0. So you consider this thing now it doesn't really do any subtraction because f of x minus 0 is just f of x divided by x. So that shows you that it's already a root.
Yeah.
And it's also like x minus what? Minus 0. So,
So you said something about our range. Like if we do f of 7, then it's already out of the Fibonacci range. I don't get that.
it means like,
I thought the Fibonacci can extend to whatever.
yeah, but this is the trace. Right? So this is this is where the prover stopped. Yes. So like whenever you're proving something like Fibonacci, you tell the prover that okay, I want just the first 13 Fibonacci numbers. So you're going to stop there. So if your proof is now requiring that you had computed the 14th Fibonacci, then that just doesn't work. Make sense?
Yeah.
Should we still do Fibonacci circuits?
Yes.
Let's do this quickly. This is the last one. So declare circuit, right?
Yeah.
Fib. Now we'll tell them what the A and the B should be. Okay? So that's the A is supposed to be a variable. B is supposed to be a variable. And then we're supposed to have like the target, that's the final thing. Also that's like a public.
What's the A and B?
A is the starting point. The 0, 1 in the 0, 1 in the normal case. Yeah.
Okay. B is 1.
Yeah, B will be 1 in this case. It could be anything. Like someone might just want to compute Fibonacci from 17 and 30, yeah. But they just care that you do the computation correctly. So then you now do the same thing. Implement, define, M31, fib for fib of variable. Now imagine trying to do this with your GKR circuits. That would be crazy.
So that will work.
How you do this with your GKR circuits? Let's finish first. Then we'll think about it. I don't. This will be crazy. So what do we do here? We need to. Let's say we're supposed to do the first. How many Fibonacci? Like let's say 100, right? First 100. Want to compute Fibonacci 100 times. No, let's not do 100 times. 100 times we won't be able to know what the answer is. Let's say 5 times. Okay. For now. So what do? We need the sum. Right? So I'll say let mut sum equal
It's sum.
so sum now let's say you have already done the first, that's like solve.a plus solve.b, right?
Why is it
Because I didn't do it correctly. So let's say we started with 0, 1, right? 0, 1. Then our sum currently contains. So basically, we have computed the third. We computed this guy now. So what are we supposed to do with this guy? We're supposed to use this guy, add it to the previous one. So that means we need some notion of like previous, right? I feel like there's a better way to do this thing. But let's just. Okay. Now what do? We now need to loop. It's just regular. It's just regular Rust. Then what do you do here? We don't care about it.
So what?
So I'm coding 5. I want to do it 5 times. If you don't want to hard code it, there's actually no way to not hard code it. Because of you should have your circuits. Circuits is static. There's no loops inside a circuit. Yes. So there's no way you can pass in, oh, I want to do it 6 times now instead of 7 times. But there's a way to now use expander to create different types of different Fibonacci circuits. So if you want it to be like 10 or 20 or 30, you can do that. You can create, but it's always spit out one already fully static circuit. But don't worry, we'll make it generic now.
So what was the short
some less than some.
The 0 to 5.
Yes.
This dot dot.
I thought you used less than.
No. Probably just like
Okay.
it's probably just this this damn ID. So now we'll update the sum, right? Is what API to add what um priv not solve the sum and sum. Make sense?
Yeah.
Yeah, the last two, yeah. So it's more like the sum is kind of like the next one. Then this one was like the top one. So we're adding those two. But then we need to update, right? So I don't know if sum should be this. We need to be careful here. We need to be careful. We need to be very careful. Let me say let's 10. This is so I feel like there's something that temp is equal to sum, then sum is not equal to this, then priv is not equal to temp. I'm coming. We'll clean up this code. Something is wrong.
Yeah.
Something is not clear. It might not be wrong.
So you're doing some
Like why can't you do this?
already on my 113. And I'm now looking again from 0 to 5 and performing some again with previous and some like
No worry, we'll clean it up. So let's see, what do we do? Let's say let A be equal to, let's try it this way. Right? Right? Then B will always be like the thing that holds the current Fibonacci that we're working on, right? So then what do? We now want to loop 5 times, right? And then we want to add A and B together and store that in B. But then want to add the previous value of B in A. Right? So what we'll do is that we'll do temp is equal to what? The current value of B. Then we will now add A and B together and store that in B, right? So API dot add what? A and B, right? Then we now update A with what? So then at the end of the day we just check, right? Does this one make more sense? Does it? Does it make sense? Cast. Okay. So we're good now. So this should be our Fibonacci. So all we just need to do is just write a test for this. I'm interested in seeing what that looks like.
How did you get off of?
Very interesting. Very interesting. Like it just
It's just like
Is that how you do? Because that's
like it's just like I think like all these things just trying to prove
no.
the addition.
those
It's not yet proven.
why is shouting interesting? Because of that number.
Yeah.
That number we have been seeing that number since now.
When that's
So that necessarily is not the sum.
No, relax.
It is just something else.
It's not. See this now, yeah? 214. These are different
yeah,
numbers.
exactly. There are two different ones.
And I feel like if we go further,
More.
it will change. I feel like
Memory slots.
they have seen the Fibonacci circuit and maybe they compressed some operations into just one operation. but I don't know how.
This thing that we are logging, what are we logging here?
The circuit, the layer
Circuit.
circuit.
What so I think we need to know what the
Yeah.
layer circuit is logging, like what this thing is, so we can know what all these things do.
Yeah, you have to look into expand. Oh, we don't have time for that. So yeah, let's just do the assignment. Right? So we're starting with 0. And then our target is what? I don't know what this will be. We did it 5 times, right?
Should we do it just now? Yeah, but the results.
We didn't solve the result. So like 0, that what we started with, and then we started with 1. So every time we run it, we get a new sum, right? And we're running it 5 times. So that was like index 7, yeah. So this is what 1. This is what. So this is like first time, second time, third time, fourth time, fifth time. So it probably should be 8. So let's just do let's make it fail first. No, it's supposed to be 8, right? So it works. Makes sense? So somehow, this is doing Fibonacci. Somehow. Like takes this and multiplies by this, takes this and multiplies by this, and then he adds. What's this?
Can we try?
Let's try. Yeah, that's exactly what let's do. Like let's say let's const 1 equals m31 dollar from this, right? Then let const 2 equals m31 from then now we start with let a be equal to what? Right? Yeah, we're not supposed to say let sum equals what? A times const 1.
Oh, yeah, different.
Yeah, they're different. So what is this? Stay tuned. This is not it. Okay, let's check. Let's assert if this is equal to m31 false. Because that's supposed to be the output now. We're trying to like compute it based on like how they wrote the circuit stuff here. Which is feeling like
Does that public, was the public meaning was not there?
so it's just confusing. But it works. So it's just like once we understand how this one works under the hood, we'll be able to know exactly what all those things are. But for now it's fine. I think we can end here.
I think you make it generic.
Well, I'm worried about my this thing though, but let's continue. So to make it generic now, that's this 5, right? So now this 5 has to come from outside the circuit. So this is not like a param, right? It's not a variable. It's now also like number of steps, right?
Yeah.
Going to be u size
Depth.
or depth, yes. Going to be u size. So now we need to use this while we are building our circuits. So instead of using 5, it's now be, but you have to be careful. It doesn't just work like this. So now you can no longer use your compilation with defaults, because of default to give 0 for the depths. U size, default of u size is 0, right? So this will give 0. So what you need to do now is now like implement something like fib, then function new, right? And then it will return self. Then you can just do like self, the number of steps equals, so you can pass in the number of steps there equals to like u size. And you can also do like u size, and then the rest of them you can just do like, I think default or default. I don't know why it doesn't allow this.
We didn't
Okay?
How is it saying it?
That's macros for you. Macros will replace this entire code, this block here,
Okay.
with all the appropriate things. So now, instead of using default again, we'll now use new, and then we'll pass in 5 here. Okay? Why this other one now? So this is assignment. At this point, we don't need when we're assigning, it means that we've already created our circuit. So whatever we put as number of steps here is irrelevant, right? Because the circuit has already been fixed. So I can still do like, okay, just so that it doesn't complain. But then now it should still pass, I think. Yo. T needs to implement copy. I think I can just do fib. Wait, I'm coming. Let me just try M31. Let me see if that works. Let me try M31 config. So let's just do T then. So ask for more things though. That's one is default. Okay, so it's building now. So it still passes, right? It created a circuit that does 5 Fibonacci's. But then if we now increase this thing from 5 to let's say 6, now the answer is supposed to be 13. So when we run this, it's going to give us false. But then if we change our assignment to 13, then it gives us true. So basically what we have now is like a circuit generator that takes in some params to know how to construct the circuit. Make sense?
Yeah, what does that do?
Which one?
It's a spread.
Yeah.
Which one? This one?
Yes.
Right.
And kind of like the rest of the fields that are not here, just do that default thing. Yeah. All right.